Hello, testing? Yeah. Everyone. Welcome to the Extending miniKanren and Relational Programming session. And I'm very glad to introduce Rafi with Beyond Cons, Purely Relational Data Structures.
Hello. Hi. My name is Rafi Sena, and I'm going to be presenting purely relational data structures. This is joint work between myself and my advisor, Nada Amin and Will Bird. Before we jump into the actual data structure stuff, I'd like to start with kind of the impetus for some of this work. Who here is, by just show of hands, has seen this textbook before? Okay. This project actually started when when Will Bird wanted to go through this textbook and implement as much of it as possible in miniKanren. Spoiler warning for those who have not read the first chapter. We don't get very far, so you don't. If you haven't implemented all the exercises in chapter 14 on dependent object types, you're still good. But specifically, the issue that we ran into started around here. So this is one of the first definitions in the entire book, and it literally defines simply typed untyped lambda calculus terms, right? So we kind of define it intentionally. Specifically, that term intentional being quite important, so I'll take a second to explain. Intentional here means that rather than list out all the possible elements of the set, we give it the defining properties that are necessary to be a member of the set, and sufficient as well. So here we give kind of a traditional smallest set fixed point definition. We say for all terms, here are the ways to construct it. You have the three kind of canonical ones. You have variables from some countable set of variable names, lambda abstractions, and applications. I imagine this is pretty bog standard to those who have seen it before, or even those who haven't. So this set is obviously infinite. There are an infinite number of lambda terms. And so intentional definitions are the better way of specifying something like that, because we can't enumerate an infinite number of possible terms explicitly. So translating this into miniKanren is relatively easy. I imagine that this definition is going to be relatively canonical to those who have seen miniKanren before. It matches pretty much one-to-one with the definition we saw on the prior page. And this works out well because, again, this is an intentional definition, and miniKanren is very good at these. It's able to give us, this is the necessary conditions for defining sets, defining lambda calculus terms. It's the kind of least set model that was brought up here naturally kind of models the Brand terms logic that is used in the smallest Brand universe used by the semantics of logic programming. So this, I think, kind of has a natural dual with for making sense of why this is kind of very easy to define. So it's this definition where we start running into a bit of a problem. So this definition defines a set of free variables of a lambda term. And so what's important about this lambda term is that with respect to a given, what is important about this definition is that with respect to a given lambda term, the set of free variables is defined extensionally, meaning we list exactly which variables are part of it. And so this set is also finite for a finite lambda term. So you can see we do some basic set operations using a singleton set, the set union operation, etc., the set subtraction operation, which is written with that / symbol. The fact that this is finite is rather important because, as again, bit of a spoiler warning, it is very important to be able to tell whether or not a term has no free variables because it's how you define combinators. So trying to define this in miniKanren is not impossible, and this is probably my best bet on how to do it. So you can see that we can't define it in the way we did before, where we just have the intentional definition. We have to explicitly reify the set of possible answers as this free variable value. Why is that? Because it would be very different, because as is well known in the logic programming community, having negation, or saying there is not a free variable, is rather difficult to define, especially for intentional sets, because that gets into a long list of classical issues with have to do negation. So defining the sets extensionally is the best way to kind of get this negation effect by saying there are explicitly none. And so I highlighted in blue the set of constructors that I'm using here. So notably, we're using set unification, a set constructor, and so then that is a procedure defined at the meta level. This is in the same sense that cons is defined at the meta level, or list is defined at in the meta level in miniKanren. And we use subtracto and union O, subtracto being subtract out an element from the set, union O being union, as is, I imagine, to be expected. So I think other than the kind of operations here, this should be relatively straightforward a translation as well. Anyone have any concerns about either of these translations? Great. So the question then becomes, how do we define these constructs? So one way you might try defining these constructs is using the kind of classical Lispy way of defining sets, which is just as lists. So we define the set constructor to just literally be the list constructor. So the set of elements 1, 2, 3 is literally the list of elements 1, 2, 3. But then, because lists also have duplicate elements and consider ordering, we need to have our own notion of unification, which is this set equal equal on the bottom here. This is defined in terms of a subset eq-o operation, which is just the inclusive subset operation. This is a relatively canonical inductive definition of this, this relation. It is definitely a correct implementation. It is naive in the sense that we have to like bear a linear time cost for checking whether or not something is a member or not, but otherwise this seems relatively reasonable. The problem arises when we try to actually use it. So in this case, this is a technically correct answer, as I mentioned before, but procedurally and operationally, we end up with a lot of issues. Specifically, we begin enumerating all possible sets in the same equivalence class. So on the top here, you can see that this free variable example just immediately begins enumerating all the quote-unquote equivalent versions of the same singleton set X, because, again, we told it to ignore duplication here, but it's still searching over the number of possible duplicates in the set. You can also see that we get multiple versions of two sets because it's implicitly reordering the same element, which of course isn't meaningful. And we can see why this happens if we look at a simple unification on the second line here. When we are trying to unify a constant set against just a fresh variable, we actually begin enumerating all possible sets in the same structure. And we can see, again, we are considering all possible sets with respect to ordering and with respect to duplicates. So this isn't a time complexity issue. I'd like to stress that quite a bit. This is a fundamental usability issue. It's not tenable to do this kind of work because A, you destroy any chance you have a finite failure, which is generally something miniKanren programs should have, and B, it entirely destroys your backtracking because now every time what would normally be a singleton result and would allow the miniKanren search strategy to move towards a different branch of the search tree will now infinitely enumerate these, and while the search is complete and will eventually find the answer, it will just be significantly slower. So how do we fix this, right? You might think, okay, sure, using lists like this is incredibly naive, right? This is like not how anyone who has a good understanding of data structures would implement a set. Maybe there's just some different data structure that we need to use. And so we might turn to kind of the Bible of data structures in functional programming land, PFDS by Okazaki, as kind of a way of defining these in a new method. So Okazaki, this work was really important for a number of reasons. Not the least of which being that all of these data structures were defined in the language at hand. They didn't need to add much to ML or to Haskell in order to get these data structures to come out naturally, other than some slight laziness syntax, which hadn't quite been standardized. So while it may just seem like, oh, we need to get a better data structure, I'm going to claim that that's not true. What we need is purely relational data structures. And that relational programming needs something that functional programming doesn't. So we need stronger notions of equivalence, and we need good search semantics. These things aren't satisfied by current data structures. And so there becomes a question of what do these data structures look like, how would we use them, and how do we find them in the real world? So one way we think this might look like in the real world is something like the work of setlog. So this is an implementation of specifically the set data structure by Dauvier et al., which that lab has a long history of work of doing kind of this finite set semantics in Prolog. So specifically the language they use is called setlog, and it defines a set of operations that crucially work as constraints rather than traditional inductive relations. So rather than mandate the data structure be in some specific structural form, it instead mandates it have some semantic form and not search over the possible structural forms that inhabit that semantic equivalence class. So can we port this to miniKanren? The underlying logic behind it looks like something like this. Crucially, you'll notice a lot of the common operations that we have in miniKanren, disunification, disjunction, conjunction. It also has a universal quantification, that for all symbol, but pivotally, it is always for all x in some finite set. That ensures that we're never going to have the problem we had before where we begin enumerating all possible sets. If we were able to have for all x blah for any value of blah, then we would have the issue we ran into initially. So what do sets look like in this world? So here is the three kinds of sets that are defined in Dauvier and how we represent them in Scheme. So the empty set is just written set here. This is the set which contains exactly 0 elements. As you saw in the axiomatization, it is defined to be an instance of a set. It is defined to have no members, and so on. The other object we have is the proper set. So this is a set which contains the elements A, B, and so on. Because this is a logic language, we aren't able to tell exactly whether or not A or B are distinct objects at a given period of time, right? One of them might be a fresh logic variable, or worse, 2 of them might be fresh logic variables. And so we have to kind of accept that there will be potentially be duplicates in our set. And this last implementation is an improper set, hearkening back to the kind of Scheme language of improper and proper lists, where the rest of the set is some other fresh logic variable here R. And so having these 3 different ways of defining things allows us to implement sets in a way that give semantics to sets in a way that seems like it makes a bit more sense. So here are some examples of unifications using this method. So here we note we don't use a set equal equal operator. We are using literally just the normal miniKanren unification operator. It understands sets implicitly. So we have at the top just defining to a fresh logic variable does the same thing you would expect it to do in any miniKanren implementation. You just immediately assign it to the fresh logic variable and move on. Unification, even against sets that are semantically the same but are structurally different, will instantly succeed, as you'd expect. And an important note is this last element here. I apologize if this is a bit hard to read, but what this says is find all Q such that the set 1, 2, 3 unifies with the set 1, 2, and all elements of Q, set P, sorry. P such that 1, 2, 3 elements unifies with P, and pivotally, it gives us several responses back. Because we're not able to know whether or not P is actually contains the elements 1, 2, or 3 yet. You know it must contain at least 3, so 3 is in all of the possible results, but we know that 1 and 2 could possibly be in there, and so we enumerate the power set of 1, 2, 3 for all that contain 3. Does this sense of unification make sense to everyone? Are there any immediate questions? Great, we can move on a bit more. So unification is not the only set constraint that Dauvier defines. So specifically, there is a relatively long list of set constraints, but they are defined in terms of these 3 primitives at the top here: non-membership, disjointedness, and set union. So set union we saw earlier as just the union of A and B is C. Non-membership is just the element is not a member of the set, and disjointedness is that these 2 sets have no shared element. I won't go through all of these, but the key idea is that if we have these 3 primitives at the top, it's shown that we can express the rest of the typical set primitives that we expect in a set library or your favorite programming language. So for example here, union plus O is the disjoint union, which is, sorry for the large text. Here we just mandate here that for any L, R, and C, or 0, 1, and 2 in the fresh logic variables, they are all sets, first off. Next, that the first 2 are disjoint. That's what that parallel symbol means. And then the union subscript 3 means that these 3 should union to each other. And that's just kind of the definition of disjoint union. So if we use this way of defining sets, we get our free variables example to work as we would expect before, where we get back a single result. And again, I cleverly defined the set of primitives before as exactly the ones that are defined by CLP set, so it kind of works without any modification. So the initial implementation of this work was done by Nada and follows the implementation not of the actual software that is done by Dauvier et al., because they have a software artifact that goes with it, but this actually implements the rewriting procedures. So specifically something like this. This is obviously you don't have to grok all of this, it's essentially how we define equivalence. So this is a way of turning the left-hand side, which is some primitive notion of equivalence, into the right-hand side, which are smaller constraints that have to do with it. And so by breaking it down, you kind of get down to the atomic constraints that we all know and love from miniKanren and can solve those normally. This is that unification procedure reified as code. I understand Scheme is like not a golfing language, but it's still quite a bit of work. And again, this is just unification. So the other set constraints are all additional code on top of this. So what the impetus of this project was that we wanted to implement the CLP set operations in terms of Michael Ballantyne's faster miniKanren. If any of you have used a miniKanren in Scheme, or I think oKanren is similarly based off of a lot of the work by Michael Ballantyne, this is kind of the canonical modern implementation of miniKanren. It has a number of fancy features, two-watch literal scheme, a more efficient data structure for element lookup and environments, a whole bunch of very nice stuff. But there are some issues that arise with it. So going back to our definition of equality here, we can zoom in on a specific one of these rules, specifically rules 9 and 10. These are how we define unification against sets. And so the pivotal point here is that there are 2 things that we normally wouldn't think of as unification results. Namely, if you look at these, that keyword any of means it's a disjunction. So unification can now cause multiple results, as we saw before. which is kind of violating one of the typical assumptions we make about miniKanren as a language, that unification will either succeed at most once or fail. And note also that we introduce a fresh logic variable here, m, and we put a constraint on it. So unification is no longer just a function from finding the most general unifier. There is no most general unifier in this case. We have to give unification an arbitrary level of computation. This kind of causes some fun issues with some of the optimizations that happen in faster miniKanren. So we can see an example of this here. So here we're unifying two sets which contain 1 and 2. P and Q are fresh logic variables. But note that _0 is found in the results here. _0 is not P or Q. This is a fresh logic variable that was just introduced by the unification, and we bind a set value to it. And so if we have something like the two-watch literal scheme of faster miniKanren, which requires that unification always just become a conjunction of primitive assignments, then that no longer works. And it requires quite a bit of kind of hackery in order to get back a lot of those semantics. So in the paper, we kind of go over a lot of these things. We add, in addition to Dovier's existing constraints, some association list constraints that allow us to do environments in the kind of typical bird-style relational interpreters. We face off against that that two-watch literal scheme idea within the disunification by using the first-order representation and optimizing it out in certain cases. We give a more idiomatic API for metaKanren and for set-based tabling, along with a few other things. But I guess this is where I will end things. The key points being that purely relational data structures improve the operational usage of miniKanren programs. They have to be reasoned about semantically rather than structurally, as we saw. They have to use lazy constraints rather than recursion. They can be implemented in modern miniKanren implementations, but challenge assumptions about what miniKanren is and how it operates. That's all I have, if there are any questions.
You have? We have several minutes.
Great talk, cool stuff. I think I recall in the Dovier et al. Paper, they talk about not just that choice of 3 primitives. One of those Dovier et al. Papers, they talk about the choice of these 3 primitives as opposed to alternate options. What happens if you did this? What happens if you did that? Is there any interesting thing to say about how that differs in the miniKanren context or alternative choices, what that would do to the implementation strategy in faster MK?
So there were a few other methods that were considered by Dovier. We didn't, they did not implement those other methods, and we didn't either. It seems pretty natural that the methods that we used for implementing them would translate over to the other ones. I'm not sure if they would give better operational behavior or better algorithmic behavior. It doesn't seem like that would be the case, at least. But I guess if there is reason to believe that, then it seems like we would naturally be able to translate this stuff without much difficulty.
All right, we have time for one more.
So you talked a lot about sets, but if you think a little bit further ahead in that, well, probably the more important data structure is finite maps for representing things like environments or stores, etc. So I was wondering if you had any thoughts about that as a case study to finite maps, but that's anything to say about that.
That's a great question. So in the paper, we actually do extend the work to specifically association lists. And so this is a kind of different way of talking about the data structures in general, where here we were using sets as kind of an abstract structure, but we consider a different way of doing things where we define association lists inductively in terms of their elements. Obviously, association lists are well loved by miniKanren programmers, but they do have limitations in that they put certain they make certain structural assumptions about the way things are ordered. And so I think natural next steps are extending this to things like finite maps and other data structures. And I think the more general next step is finding out how we can define these without baking them into the interpreter, right? Because these constraints now must be implemented as primitives in the interpreter. And so if we want tries or maps or any other abstract data structure, it requires some method of doing this encoding, and it's not sustainable to just write a new miniKanren implementation every time you need a new constraint.
All right, thank you for the questions. I think we are out of time. Let's thank the speaker. Thank you, Rafi. And let's welcome Dmitry Volkov with Committing to the Bit, Relational Programming with Tensors and SAT Solver.
Just testing this while it loads. Looks like we're good. Should be fine. All right. All right, thank you. So this is Committing to the Bit, Relational Programming with Submarine Arrays and SAT Solving. So I'm Dmitry, and we'll get going. All right, so the topic of our research is miniKanren, which is a new variant of miniKanren. So just I'll go over some of the differences and explain more what they mean and how they look like later. All right, so one of the core main differences is that as opposed to miniKanren's top-down evaluation, miniKanren employs a bottom-up evaluation strategy more similar to Datalog. So similarly, miniKanren computes relations as functions on streams, sort of essentially. miniKanren computes arrays, multidimensional arrays as relations. miniKanren is dynamically typed usually with S expressions, but miniKanren is statically typed using algebraic data types. miniKanren is usually unweighted, but miniKanren is weighted, and we'll talk more about what this means. And where miniKanren is often a shallow embedding within Scheme, for now miniKanren is a deeper embedding. All right, so just a motivating example. Here's how you might implement a coin flip relation in miniKanren. So it's just either heads or tails. No real surprise there. So as I mentioned, in miniKanren, we have algebraic data types. So we either have unit types, sum types, which are either left or right, product types, which are pairs. And so a Boolean could be defined as a sum of two unit types, as shown there. So a coin flip in miniKanren looks a little different, but it's essentially the same thing under the hood. So we're either calling lefto on the coin variable or righto on the coin variable. So lefto and righto are they're sort of relational constructors for the left and right. They're the relational versions of the left and right constructors for some types. So note that we need to introduce a fresh unit variable. That's because the lefto relation has 3 arguments for the internal type. So we do need to pass in the internal unit variable. But besides that, it's pretty much the exact same thing as up here. All right. Do you want me to go back? Or?
Yeah, what's C?
C is the coin argument variable, yeah. All right, so as mentioned, another core feature of miniKanren is weights. So we can use the factor goal to add weight to a branch of a program where the weight is drawn from a semi-ring. So quick reminder on semi-rings if you're not familiar with them, but they're essentially a set with addition and multiplication operations where multiplication distributes over addition. There's some other constraints, but that's what it boils down to. So for example, real numbers with multiplication and addition, obviously, or Booleans with or as addition and as multiplication. All right, so we can do a weighted coin flip. For each of the left and right cases, we can conjunction on factors. So here we have left occurring with weight 0.7 and right occurring with weight 0.3. Yeah. So miniKanren supports recursion, as one would hope. So as an example, we'll do transitive closures or graph connectivity. So we can represent a graph as a relation. So here we have 0 is connected to 1, and 1 is connected to 0. So you can see that it matches the graph. We can express connectivity with this connector relation. So either there's a direct connection between two nodes in the graph, or there's some intermediate node that connects the first and final node arguments. So if we evaluate this over the Boolean semi-ring, we just get connectivity. So 0, I guess I'll point. Here we go. So 0 connects to 0, so we see a true there. It connects to 0, but 0 connects to 3, it does not. So we see a false there, or a bottom. But if we use the min-tropical semi-ring instead, we get the shortest path length. So we can see 0 to 0 has length 2, I guess assuming these edges have weight 2, which we need to encode with a factor. Sorry, weight 1 with a factor. But yes, okay, 0 connects to 0 with 2. 0 connects to 1 with 1, but 0 does not connect to 3, so we give it weight infinity, which is it's the the identity value for the minimum composition law. All right, so how does this end up working under the hood? So relations compute multidimensional arrays. Variables are specific dimensions of these arrays, and goals are operations on these arrays. So let's focus on the first two. So if one dimension of an array is a vector, so we need a way to represent values as one-dimensional arrays. So for example, I'll do this pair of Booleans value, and we'll see how that gets translated to an array, because it shows all of our different types. So pair left sol right sol is a prod of two sums of units. So sols just get compiled to the vector of a single element with the one element of the semi-ring. Left and right gets translated to direct sum of vectors. So we have our sol is 1, so we have our sol there, and it's being vector direct summed with a 0, which is the size of the other side of the type. So yeah, we fill up a vector with the size of the other side of the type and add it on. And then pair is handled with Kronecker product of these vectors. So here's what all the encodings for the type look like. We can see that for each value of the type, we get a vector that has a 1 in one location and zeros in all the other locations. So values become one-hot vectors, and the size of the type corresponds to the size of the vector. But what if we have more than one vector more than one 1 in the vector? As mentioned, relations compute n-dimensional arrays. So this can be seen as a relation where the pair of two lefts or pair of two rights succeed, because the 1 in the first entry corresponds to pair of two lefts, and the 1 in the last entry corresponds to pair of two rights. We've got both of them there. So it's a relation where they both succeed. All right, so relations compute arrays. Non-zero entries denote successes, and 0 entries denote failures. So what do relations look like on more than one variable? So as mentioned, variables are specific dimensions of these relation arrays. So if we have a relation over multiple Booleans, for example, then x and y each get a dimension of the relations array. And so you can see it's a 2x2 array, because each dimension corresponds to a Boolean, which has two values, then two Booleans, so two-dimensional array where each dimension has size 2. So if we, for example, consider the relation where x equals y, then we what looks like a unit matrix where there's a 1 where x and y are both true, and a 1 where x and y are both false, and zeros in the other spots. Or if we have a relation where there's only a condition on one variable, we can see that, so we're doing true OX, we can see in x is, we only have ones when x is true, but we have ones in either slot for y. All right, so how do we use these relation arrays in practice? As mentioned, goals are operations on these relation arrays. So there are essentially two classes of goals to worry about. There's low-level relations. So like I mentioned, the constructors for the types we have, equality, disequality, which is pretty nice, succeed, fail, factor, and then applying relations, and then goal combinators, which are conjunction, disjunction, and fresh. So for low-level relations, we generate generate the array corresponding to that relation. So as mentioned, equality looks kind of like a identity matrix where we put ones in the places where they're equal. So implementing disequality is super easy. We just put zeros where they're equal and one where they're not. So that's very, very nice. Lefto and righto correspond to unifying the left and right parts of the array. So it's, so they correspond to unifying the left and right parts of the bigger variable with the smaller variable. It's kind of hard to show Pero because it's a 3 argument relation, so there is a sort of third dimension, but it's a similar sort of thing where it goes into the structure of the variables and unifies the right parts with each other. And then factor just fills the entire array with the value. Succeed corresponds to factor 1, and fail is just factor 0. And then what relation application does is it unifies the arguments of the relation with the values of the variables in a pre-calculated relation array. So we'll explain what that means. We'll go into more detail about that later. So then there's goal combinators. Conjunction just corresponds to multiplication. So again, you'll remember for Booleans, and is the multiplication. So conjunction just generalizes that over any semi-ring. Disjunction is addition. Again, for Booleans, or is the semi-ring addition, so just following the same thing. And then fresh is summation over the variable axis. You can sort of think of it as a disjunction over all the values of the variable. Yeah. All right, so what about recursion? So we assume that the relations fail until we have more information about what they need. So as I mentioned before, when we call a relation, it uses a pre-calculated relation array, but in the case of recursion, we don't necessarily have that pre-calculated relation array. So we start again, and we repeat this process until there's no new information, so we calculate by fixed point, similar to data log. So going back to this transitive closure example, we'll do a step-by-step walkthrough of it. We start by the all 0 case. So infinity is 0 for the min-tropical semi-ring, so we start by assuming there's no connectivity. Then we fill in the information we have from the graph, because we can already calculate that. So we have a 0 is connected to 1, for example, just based in the graph, so that shows up there, and so on. So then we can consider intermediate vertices. So we know 0 is connected to 1, and we know 0 is connected to 1, and 1 is connected to 0. So then we can add those together with the intermediate clause and put a 2 there, and we get the 2 there. Similar for the other entries. We reevaluate it, there's no new information, and we are all set for calculating this connecto. All right, so this is, again, bottom-up evaluation, similar to how data log does it. All right, the end. But what about committing to the bit? This presentation didn't really have any jokes. The joke is that there are no jokes. The joke is the meta-humor that the jokes is that there are no jokes isn't really that funny. The joke is that the meta-humor isn't that funny. The joke is that the meta-humor still isn't that funny. We have computed the joke by fixed point. The larger type and right is just pair of false with its information packaged up. So the smaller type of the smaller contained type of the sum type needs to get coerced into the larger type. So for example, let's consider a nested sum type with 4 total values, so it's just a sum of 4 units, and this gets compiled to a prod of 3 booleans. So working from the bottom up, right sol gets compiled to false. Wait, what's going on there? Okay, there we go. Right sol gets compiled to false, left sol gets compiled to true. So we have a special case for handling the left and right sol just because they're easy to map directly to booleans. So again, sum unit gets compiled to bool. All right, one level up, the right gets compiled to a pair of false and false. So here, the right of left of sol gets compiled to a pair of false and true. Again, same sort of thing. But here's the interesting case. We have this left of sol, and down here, so sol is smaller than the bool type that we have as this orange part. So in the case we just have a sol, we compile it to true, or we fill the whole thing with trues when we need to coerce a sol type. So then one level up, the rights get compiled to falses, the left gets compiled to trues, the sol get compiles to just filling the whole smaller type with sols, and we're all done for compiling this type. So sum unit, the type we just assert that the tag is false and unify the contained type. And then lefto is pretty much the same thing, except that we're testing for true, and we're using a coerced equals rather than a raw equals. So miniKanren does generate type-safe code to do these, or it tries to generate type-safe code to do these coerced unifications, but then lefto and righto just become true and falso with this unification. All right, so note that, so again, it's inefficient in how it, I was trying to remember the point I was trying to make here. So because the compiled type does have more values than the smaller type, we also need to make sure it doesn't inhabit invalid values that fit into the type. So miniKanren also generates code to make sure that this prod bool bool in practice. All right, so for future work, polymorphic relations. So right now, our relations are mostly restricted to the type, but it should be possible to make them polymorphic while only using one relation array per relation rather than generating a new relation array for each type. I guess sort of intuitively, we already kind of do this for equality and the primitive relations. So we just want to try to figure out how to get this to work for arbitrary relation arrays. And then once we have that, hopefully it should be more straightforward to get recursive types, which we currently do not support, but having them would obviously make the language a lot more useful. Potentially using an SMT solver to handle the recursive cases better and potentially handle non-Boolean semirings for when we're doing that kind of evaluation. Quantum computing annealing. So these relation arrays kind of intuitively look like superpositions of the argument variable values. And with relational programming, we get reversibility sort of for free just by swapping the orders of the arguments. So it kind of intuitively feels that this could potentially be a good, interesting paradigm for expressing quantum computations. But there's a lot of work to be done to see if it works out nicely or not. And then figuring out how different semirings behave in the system. I think it's possible to come up with semirings that do not converge over fixed point with this method. I think there's already existing literature in the data log sphere about what works and what doesn't, but just need to look into that some more. And yeah, just applications are always useful. All right, so I think that is about it with miniKanren committing to the bit, relational programming with string arrays and SAT solving. Any questions? And thank you. Yeah.
like array programming. I don't know if you have any comments on that or if that was inspiration or anything.
I guess I wasn't thinking too much about array programming in terms of sort of intrinsic connection. It's obviously implemented using array programming, and I was an array programming enthusiast at some point, so I don't know if maybe there's some subconscious connection there. But I can't think of any deeper connection beyond what I've shown here for now, but that doesn't necessarily mean there's not one there. Yeah.
Hi. So you're using just dense arrays to represent all the stuff multidimensional. Have you thought about using a sparse representation? Because it seems like a dense representation is not going to scale up to like 32-bit integer variables or natural numbers, which would be fine.
Yeah, I agree 100%. We used a dense array here just for convenience of an initial implementation, but I definitely want to switch to using sparse arrays or, yeah, but I'm trying to think about other representations that aren't even necessarily arrays that could do the same sort of thing. Sounds good.
Hi, great talk.
Thank you.
You had shown an example earlier where you implement numbers. How are those translated into bit streams?
Yeah, so the, I think I'll just scroll all the way back. So the numbers are used for the graph to represent nodes in the graph. And those are just translated as sum types of a fixed size. So it's more of a notational convenience here than, I think I went too far. No, I didn't. It's more of a notational convenience just to keep it on one screen than anything else. Again, once we get recursive types and hopefully the nice one representation of an array one array representation per relation, we will hopefully get something fancier, but for now it's just a sum type under the hood. Yeah, finite sum type.
My first question is about you try to compare with some other logic programming program that solve some problem because it's pretty common in logic programming.
Yeah, so we haven't compared it to other logic programming languages outside the ones we showed. We did compare to a hand encoding of the SAT problem, and it is a lot less efficient of an encoding that we generate than a hand encoding of the SAT problem. But it does generalize nicely to pretty much any miniKanren program, which is nice.
Also, there are logic programming that combine with SAS tooling, which is called answer set programming.
Yeah.
And it works very well on recursion because it's essentially data log encoding. So yeah, it might be something you are looking for. I personally don't think that SMP is working very well on recursion, but ASP might be the solution.
Okay, that's good to know. Yeah, we did read about answer set programming, and I think there's some extensions of miniKanren which incorporate answer set programming. I guess here we're kind of going for a different approach on it, but that's definitely good to be aware of, and it's on the radar, and it's something I'd like to look into more. But thank you.
All right, thank you everyone for your wonderful questions. To thank the speaker. And let's welcome Eridan with an empirical study of rational tree unification for miniKanren.
Hello, my name is Eridan, and I'm going to present here my work with Dmitry Kosarev and Dmitry Buluchev about empirical study of rational tree unification implemented in miniKanren. Motivation. Our motivation is simple. We just want to use miniKanren to infer recursive types. And we have globally two options. One of these is just re-implement all unification in terms of miniKanren, and the second one is to extend miniKanren interpreter. Previously, we already have presented a way to to extend miniKanren using some non-relational way, using hooking and occurs check. It looks like that. So if we have a favor of unification due to recursion, we have we allowed user to provide an alternative answer, and it works, but poorly. So now we want to try to implement complete unification for rational trees. And the second small motivation step is because some relations may become slower because of occurs check. Okay, what about history? And we have occurs check, and some provoke interpreters have no. We know that this isn't sound, and because of this, when Comrie presented his rational tree model that is just Herban tree model, but with low to recursion in trees. Okay, what is rational tree? Rational tree is just like infinite Herban tree, but where we have only a finite number of subterms, subtrees. Okay. How we do unification? We have studied already existing unification algorithm and reformulated it in some more convenient terms. First of all, instead of substitution, we need to introduce equation systems because we need to allow recursion that isn't possible in substitutions. Nextly, we need to define some intermediate terms. First of all, we introduce head trees that is just a functional symbol applied to variables. Equation is some construction like several variables equates to one of them and possibly to head tree that is right hand side. Equation system is just a finite set of equations with disjunctive left hand sides, and additionally we need to use state to introduce fresh variables. Okay, we need to define some basic operations. First of them is union. Union is a function that unions two equations in the given system and return a pair of right-hand sides. Equations are identified by one of variables, and if there isn't such an equation, we need to assume that there is a trivial one. Okay, let's consider an example. If we need to union variables x and y in empty system, we just get a system with one equation with unified unioned variables on the left-hand side. Similarly, if we have already some equations, some different equations for x and y, we just here we union x with z. We just add z to left-hand side of existing equation of x. And finally, if we have, if we need to union equations that both have associated right-hand side had 3, like here we have f of y and g of z. We union them and preserve. Oh, I'm sorry. Preserve one of right-hand sides, but return both right-hand sides as a result of union. And now we can start defining our unification algorithm. Is the first two rules acts for two variables, and in the first case, if we have union to variables and it doesn't return right-hand side, it means that union was already does all work of unification. And if it returned right-hand sides, pair of right-hand sides, we need to just unify them. So the main point here is that we firstly union variables, and nextly we unificate them right-hand sides, unlike conventional unification algorithm. Okay, I think, yeah. Nextly, we need to define more basic operations. Find operation just returns right-hand side of an equation. So if we have one system of equations, we may we may get first equation by variables x and y, and second equation by z, and something else non-existing equation will return for us trivial one. Okay, and bind is just a function that allows us to replace right-hand side of equation. Okay. Okay. Next two rules of unification is what we need to do when we faced with one variable and one non-variable tree. Firstly, we need to find the right-hand side by variable x, and if there is right-hand side already. We need to just unify it with the given second tree, and if there isn't one, we need to bind the given variable with the given tree. And there are caveat, so we need to split the given tree on intermediate intermediate equations because we may get non-head tree, and but we need to place in the equation system only head trees. Rules for them for this looks like that. So we just when we have already right-hand side, always easy. But if we don't have, we need to introduce fresh variables, them bind, then unify these fresh variables with subterms, subtrees of the given tree. Okay, and finally, we need to swap arguments if it x and t2, and finally, like in the conventional algorithm, we forbid different functional symbols, and for same we just unify arguments. Okay, let's consider an example. If we have such a query like on the screen, we will hang in a conventional algorithm. Why? After the first two conjuncts, we have substitution like that. And when we try to evaluate the last conjunct, we will hang because of nature of system, or not nature of substitution. Firstly, we find x. Secondly, we unwrap f. Find y, unwrap f, and loop. In our algorithm, we firstly consider first conjunct. It works like that. We need to add an equation for x firstly, but we have subtree here. And because of that, we need to introduce a fresh variable and unify it with this subtree. Nextly, we unify, and finally, we need to just union a fresh variable x2 with x, and we have system like that. So we have splitted this complex tree on two equations. Similarly, we may solve a second conjunct, and finally, when we need to solve the last one, we firstly find x in system. Nextly, we unwrap f, and now we firstly union x1 with y. Now we just unwrap, union, unwrap, union, but we don't need to union something here because x1 was already union with y that was already unioned with y2. Okay, I think we may continue. And an important feature of rational trees is having finite representation. Finite representation is just a graph graph that consists of tree and possibly links to some trees back references or cross references to compress representation. And the number of nodes in the minimal representation always equals to the number of different subtrees. And every rational tree have infinite variety of finite representations, obviously. We use mu notation for finite representation of rational trees. To do this, we introduce a new syntactic form to allow back references in terms. For example, mu x f of x represents this tree, this minimal representation exactly. Just mu x, oh no, I'm sorry. It isn't, I'm sorry. It's a different tree. Okay. Mu syntax isn't used inside of solver, but we need to use it to produce answers because it's only a way to represent rational trees as terms, as finite terms. Okay, for example, we may consider variety of representations for one rational tree, and we may see a problem here, but it doesn't. Oh, I'm sorry. Okay. Finally, how we get these terms? Given the system and the variable, we need to extract mu notation representation for x. Similarly to substitution application, we need to traverse system of equations, but we need to track encountered variables, and when we have encountered one variable twice on the path, we need to don't extract it twice, and then on second place we need to just return x or the variable, and on first occurrence we need to wrap it in a mu binder. For example, if we have such a system and want to get mu image for x, we will just unwrap firstly x, get f of x1, unwrap x1, get f of x2, and unwrap x2 to x, and we already seen it. Because of that, we just place here x and wrap the whole term in mu x. Finally, we have implemented this algorithm in miniKanren in several ways. And key point here that if we have algorithm that don't hang on recursive terms, we may consider a different unification when we works only with finite Herben-trees, but don't do a cross check on the every step, because we may we may work with not only finite terms. And we have considered some ways to implement it. Trivial one is just like a classical. Simple is we check variables right after the wall unification. The wall one unification conjunct was processed. Follow is checking after the wall run. Multiplicative is similar to full, but additionally we do cross checks every m steps, where m is doubled after every cross check. And finally, square root is like multiplicative, but m not doublet, but is assigned to be a square root of size of equation system, and we don't check the all of variables, but only introduced from the last, no, not introduced, unified since the last cross check. And all of these ways shows demonstrated the worse performance than trivial. Finally, we have evaluated our unification algorithm using our type constraint solver, and for majority of tests, nothing changed. Here we may see these tests not changed because of logarithmic scale, but for slowest test, we have reduced time from 21 seconds to 8 seconds. Here we may see results in a short list. Thank you for. I am ready to answer your questions.
Thank you, Eridan. We have time for one small question.
Could you repeat? I don't hear.
Do these trees have any correspondence to tree autonomy? Do these trees have any correspondence to tree autonomy?
This sounds like it might be a
I
longer explanation.
think it could. I think I don't. I cannot answer in time. I think it must be later. I'm sorry.
Any other questions? All right, let's thank Eridan for his talk. And let's welcome Shirt with concurrent miniKanren.
All right. Welcome, everyone. I'm going to talk about concurrent Kanren, which is a project that I did to figure out how we could do parallel execution for miniKanren. So my name is Sjoerd Dost. I've studied AI. This was 10 years ago, so no one currently understands what AI that I studied is anymore. I am this was 10 years ago, like I said, and after that I went on to become a software engineer. So I work at a company called Flower in Stockholm, and they deserve a shout out because they were graciously supportive of me being here today. A bit more about me, programming languages. I work in Go or Golang, have been doing so for the last 10 years. And at uni I fell in love with Prolog. And more recently I've been looking into Lisp more and more, and I think between the three of those you get concurrent logic programming from the top. And that's what I would like to talk about today. So miniKanren is the logic language, and then let's see if we can learn something from concurrent logic programming and bring it to miniKanren. There's a bit of a back motivation in that I found this quote after starting the project, but I think it suits really well. So this is Will Bird on the miniKanren homepage talking about the differences between miniKanren and Prolog, where at some point he mentioned that, you know, in theory, it would be very trivial to parallelize miniKanren, right? Of course, it's not actually trivial, but you know, it sounds really, really interesting. So I would like someone to look into this. And I found this quote after I started looking into that, and I thought it'd be cool to show. This is what I've tried to do, and I'll talk a little bit about how far I got. So the goals of the project I did was to run miniKanren on multiple threads in a meaningful way, where main goal was to maintain the logical order of results. So if you imagine many threads doing partial computation, you would get maybe randomly the results back. That's not something I wanted. I wanted to keep the order as if it was coming from a single thread execution. And ideally, I would find a way to show how to support a concurrent form of miniKanren that could be implemented in any other language. So it wouldn't just be me with my hobby project, but it would be actually contributing to this broader community. So here's a few motivating examples that I found to look into, because when you talk about concurrent logic programming, there are two main candidates for running stuff in parallel. You would like to look at disjunction and conjunction. So the idea with disjunction is that, you know, if I have x can be 5 or x can be 6, or any sub-goal, I can run both of these sub-goals in parallel and then sort of bring back the answers from each into the main answer. Here is an example from microKanren, which is the main form of Kanren that was basing this on, where we have a disjunction, and then immediately we also have an infinite stream. So we have 5s determining an infinite stream of x can be 5 and 6s for 6. And if we run 9, we get this 5, 6, 5, 6, 5, 6 out. And you can imagine that each individual node of the tree that represents can be calculated to present, for example, in the main top-level disjunction of that run query, you could have one thread supplying an infinite supply of x equals 5 answers, and the other one would be supplying an infinite amount of x equals 6. And you bring them back together and you get this, and here you can see that this sort of order where you switch between one and the other goal in the disjunction, that's exactly what I wanted to keep. So if we just naively somehow manage to run these two sub-goals in parallel and they start spitting out answers, we would have to interleave them fairly to get this back. There's a problem, though, at least in the microKanren implementation, of generalizing disjunction over more than just two goals, which is that due to binary trampolining, you start favoring one of the sub-goals over the other, because this run query here, so I now have 7s, similar to the 5s and 6s that I had. This disjunction plus actually rewrites to a disjunction over 5s, and a disjunction over 6s and 7s. And that 6 and 7 will supply 6 and 7 on and off. And then the main disjunction is going to alternate between 5 and the 6 and 7 stream. And so you're going to see that the 5s are being overrepresented in the main answer, when naively coming into miniKanren, I would have expected something like this to give me 5, 6, 7, 5, 6, 7, etc. So this is one thing that in writing disjunction in this way that I just mentioned, I wanted to also take on. And then we have an example in conjunction where this is showing how if you have a goal that will always fail, such as this one does not equal 2, then we have a problem in conjunction over that goal and an infinite stream where if the order of the sub-goals matters, which we would like to not have. So a conjunction over Phalo and 5s will give you the empty set because Phalo immediately fails and the conjunction gives up. But if we do the same thing and we first apply an infinite stream, we will forever try to get a new answer over the infinite stream and never reach the obvious, hey, this will never work answer that's applied in the other sub-goal. And here I had the intuition that, you know, if I run these two goals in parallel, I can immediately evaluate the other one as false, no matter the order. And if I somehow manage to bring that information back into the main evaluating node, I might short-circuit the entire evaluation. So those are some examples where, you know, I started looking at these examples in miniKanren and thought, okay, if I have some kind of parallel execution, this might be interesting. And then I started writing miniKanren in Golang, mainly just because this was my comfort zone, but also because it has some good tooling for evaluating concurrent programs. And the intuition that I took just to get started was, what if we very, very granularly embed concurrency into this whole thing? Where what I did was taking intuition from the actor model and take all of the goals as actors that maintain their own stream of answers. And you can see that here. So here is the disjunction function. It takes two sub-goals and it returns you another goal, the goal that actually is disjunction. That goal is a function. Goals are still functions of a state that return a stream. And then the way that I did here is that we create a new stream, and then in a separate thread, we run the m+ function that maintains the answer stream, the output stream. And it maintains it taking a reference to the stream that was created, the stream that will represent this list of outputs from the goal. And it takes goal 1 applied to the state and goal 2 applied to the state. So it will apply its sub-goals to the state that was put in. And so it takes two sub-streams, because these are applications, as for their inputs to the m+ function. And then that's going to run off on a separate thread, and then it will return that stream handle. Yeah.
This is just a question about the semantics of Golang.
Yep.
Does the application of G1 to ST and application of G2 to ST occur in the new thread, or is it just the application of m+ to the results?
These are evaluated before the function is actually run into a new thread. So this thread where this function application, the disjunction goal is set up, that one will evaluate it and then hand off the evaluated arguments to the new thread to start working on. Yeah. And so the parallel here is that if you have a miniKanren query, you could see it as a tree of evaluation, or in the single-threaded version, you could see just the call stack of functions calling other functions. And here I am representing each node in the search tree as a separate actor, maintaining a stream, running in a separate thread. And you can already see, yes, okay, Go has concurrency primitives that are kind of nice, and you can spin up a lot of Go routines, but still this is a crazy amount of overhead, right? But this was just to get started. And this is what m+ looks like if you then actually implement that. Well, this is somewhere between pseudocode and the actual implementation that I ended up with, but just the intuition to get you started. So what does m+ do? Well, it first waits for another actor to request a result from this stream. And then once it gets that, it will tell its first its child, hey, I want a result from you. And we wait for that result. And if we don't get a result, then the first sub-goal was not productive. We can give up on that stream, and we can say, okay, all further results that are on the output stream of the disjunction will now be found on the stream 2, the second child, which I've called forwarding, because my initial implementation was literally just continuing to still ask from that second child and then just forwarding up to the parent. But if we do get a result, we can publish that result onto the output stream. And then we continue M+, and here's the binary trampolining where we swap the order of the two subgoals. And since this happens in a separate thread, we basically have an actor waiting on a message saying, hey, I want more stuff, only then evaluates and then publishes it back if possible. And what you get to play around with is, what's the timing of all of this? When do we actually evaluate in all of these different threads? Do we start processing before we get a result? And this depends on how much you want to support infinite streams. If you don't have infinite streams, you can probably anticipate, hey, maybe I get the next request, I will just already evaluate the next answer. If you start doing that with infinite streams, you start going out of memory really fast. Here's delay. So delay is now also yet another message to a stream. If we delay a function that creates a goal, we don't actually, like we did for disjunction here, we don't immediately evaluate it as in apply the state. What we do instead is we return a function that will create the stream handle immediately, but then it will handle that stream with this following function. The first time you get a request, you don't really do anything, you just send a delay message back. And then if you still get another request, like, no, I actually want another result, only then do you even evaluate the goal and then apply it to the state. And that's what you supply. And here again, we're forwarding because the delay is it's reified as a separate node. Let's see. You can see here there's parents now suddenly involved, where previously I didn't have them on the slide, in requests here. And the reason for that is that your parent might change. If you are forwarding, or if you're a stream that, for example, M+ here says, I will forward all of the results from my second child onto the main stream. Well, that second child is not really aware of who is asking it for results. And to get away from half of the search tree just being nodes forwarding results, we can short circuit that and just connect the grandchild and the parent requesting. And the way that we can do that is by just the parent saying, hey, I am this person asking you now, so please return me here on my inbox any answer you might calculate. So we have messages going back and forth. These are the message types I ended up using. There's these interesting combinations of messages that make it so that we don't have race conditions between knowing whether you got an answer from a stream and whether that stream was actually productive. I found this also in, don't remember the paper by heart, sorry, but it's in the references in the paper I wrote. In evaluating semantics of miniKanren, where this also comes up as sort of separate cases in the typing. But you can imagine that a unification, for example, either produces an answer or it doesn't, but whether or not it does, it will also immediately not be productive afterwards. And so unification sends a message of state and close or close to the person, to the actor requesting a value. And similarly, we can forward, or we can forward with an answer saying, hey, I got an answer, but I know that the next time you want to request something, don't ask me, ask this other stream. And then there's a few improvements further that I made to get this to work. So substitutions, naively association lists, If we try and speed it up a little bit, we get to something like hash maps. But if we're doing work in multiple threads, we're going to get race conditions real fast, so we might not want that. Instead, what I found to be very useful is these immutable AVL trees with structure sharing. They solve a couple of different things. The main thing, so they're immutable, so I can share them between threads without having to worry about modification. And then if you modify them, because I can obviously do this with a hash map, but then anytime I send it like an immutable hash map, I have to copy the entire thing. This gets really, really expensive really fast. So instead, with these immutable AVL trees, what you can do is you can only change a couple of nodes in the tree and use a pointer to the main tree that you deviated from to only send the reference of the changes that you've made. And this reduces essentially this copying operation from something like ON to O log n, which is very, very impactful. The number of Go routines, as I mentioned, was a big problem, all this parallelization overhead. So I used a worker pool pattern that roughly mimics, not roughly mimics, it just uses a bounded number of threads instead, and it sets up these actors not as actual actors that are getting messages, but it has pieces of work that essentially, if someone asks an actor for another result, it will put this on a task queue, and then one of the routines is going to actually pick this task up, calculate whether there's a result, and publish it back, and maybe trigger a new piece of work or multiple pieces of work to be queued again. And this is how evaluation proceeds. Then there's generalized concurrent disjunction. So I managed to write a disjunction that actually writes all of these, runs all of these subgoals in parallel. And what it does is it essentially buffers up an answer from each of its children and then serves from the buffer. And if it runs out of buffer, it will go by each of its children again that were productive last round, and then do it again over and over. And the conjunction with short circuit evaluation, the way that this ended up looking like is it's running two things. It's running the full conjunction as a stream, and then it's running the second child separately. So it's doing more work, but if the second child doesn't produce an answer immediately, you get to cancel the rest of the evaluation and just throw it out. And that solves the conjunction example that we saw before. Here are some of the results. Now this is a very funky looking picture, mainly because of the single threaded example. What I used here to evaluate some of the results was a query that was looking at two numbers and the amount of ways that you can sum two different numbers together to get that number, which I expected to be a linear evaluation, but you can see that the single-threaded evaluation here is all over the place. I did not manage to figure out why that is. I have to show it here. The single-threaded case was there, and it did some really weird stuff. I have to follow up on it. But the more interesting parts, I think, are the message-based and the worker pool implementations. And then there's faster miniKanren that was mentioned earlier today as sort of the baseline. So we have faster miniKanren over there. We have the number as an input that I was saying, hey, give me the amount of ways that you can basically factor this into two summons. And then the time in seconds over there. The message-based evaluation of this problem was the one that creates a Go routine for every single node in the search tree. So you can see at some point this is actually not maintainable and it starts becoming really, really, really slow. Whereas the worker pool implementation follows the faster miniKanren fairly neatly here. Yeah. That's about it. Any questions?
This is super interesting work. Did you do any level of static analysis to try and prevent spawning of new threads on, so for instance, on something like if I have a conjunction of several unifications, given that unifications, at least under the traditional miniKanren scheme, are relatively inexpensive, I can run each of them. It kind of becomes wasteful to run each of them concurrently, especially if you're doing the scheme that you had mentioned where you run the first and the second and the third and the fourth all in different threads. Had you considered any level of optimization to ensure that you don't fork off different threads on things that are very likely to come back pretty immediately?
Right. I did consider it. I didn't look too much into it. I know that there is work on online figuring out how to, for example, order conjunctions to do similar things with static analysis. The furthest I got was just playing around with, hey, if I swap this disjunction plus out for a concurrent disjunction plus, does anything change? So I found some, if I remember correctly, quite impactful changes in terms of the overhaul performance doing that way, but I didn't find a good rhyme or reason yet to. So I think the main reason for that is that I worked a lot on this everything as a go routine version and got the worker pool version in quite late. And so only then did I get a real toggle on this. I think it'd be future work, but it's a really interesting direction, yes.
Hello. Yeah, it's very good work. Thank you so much. My name is Xiang Yu from Arizona State University. I have 2 questions. First thing is I want to confirm my understanding of your approach. Are you using the publisher and the subscriber in distributed systems? And just because the Go provides some like the infrastructure to allow you to do that. So for example, if you want to implement into other languages, so I need to implement this kind of publisher and the subscriber things, right?
It's a very good question. I used the Go primitives with channels for the, let's see, the message-based implementation everywhere. And so that one, yes, you would have to do some work to actually replicate this if you'd write in a language that didn't have support for those. But the worker pool implementation, if you just have your normal threading and you can put stuff on a single queue, then that's all the support you'd need. So any more interesting like publish-subscriber interactions that are specific to a certain language, I don't think are necessary.
Okay, so for example, like one approach I could do the publisher, subscriber. The other one is like the piece rest stuff, like the worker pools you're using, right?
Yep.
Okay, thank you. Second one is like why you need to forward, because you create, you one goal, you have 2 sub-goals, right? And you want them to run parallel. And one failed, and then one you run the second one to forwarding. So this more like sequential to me.
Like that. Yeah, I mean, if you look at the single-threaded case, if you look at the disjunction, if it finds the first goal unproductive, it will just basically call the second function, second goal as a function and just make sure that the results get there. The way I set this up is that all of these nodes, they didn't really know about each other. They might have a direct handle on the childs that they spawned. But so that way, I left all of these sort of dead nodes in the tree where, you know, okay, I know that all of my results, since I am disjunction, but all of my results are just going to be the exact same as the second one because the first one I gave up on. And yes, it will find that out at some point. But past that point, it's very inefficient to sort of go through this node that just says, oh yeah, if you want a result from me, just find it here, and then I'll send it back to you. So connecting those 2 back and sort of removing that intermediate node, that was forwarding.
Okay, so basically you are just constructing the graph, but once you construct it and you start running, they're still like running parallel. So just make sure like, okay, the child's forwarding the message to the parents.
Yeah.
Oh, thank you so much.
We have time for one more question.
Jason Heeman, can you speculate on what we're going to hear about in miniKanren Workshop 2026 from this project?
For me or in general, I would hope that a lot of people would look into this and see, hey, can I actually also do something like this in my language or my variant of scheme? For me, personally, I don't know how much time I will dedicate to this since I work 40 hours a week. And I did this work while in between jobs started the year. But thus far, I have found time to do it, and it's actually really fun, so who knows. And I think one of the main things I would like to look at is what was mentioned before. Like, can we more surgically target places in the search tree where this parallelization actually is useful, instead of sort of the overkill of doing everything? No.
Since I'm not as familiar with Go, what are the performance characteristics of the threading in this environment? Are we running millions of threads, or is this something that we have to scale down?
So in the message-based one, we have one lightweight thread called a Go routine in Go per node in the search graph. So that's many, many, many. In the worker pool version, I was running this with 10. So like one per logical core.
All right, let's thank the speaker. This concludes our session. We will meet after lunch. Good luck.
most ambitious of our time, the Libra phone, the Freedom or Liberty phone. The modern
Up next, Kate is going to be telling us about typed embedding of miniKanren for functional conversion. Kate.
Thank you. I think there is some noise.
Is it the ice machine back there?
Ah, okay, okay.
You want to unplug it?
No,
We
no,
stopped it. No, it's like, but keep an eye.
I just thought that maybe I'm doing something wrong, right? Okay, I'm going to be presenting my students' Igor's master thesis on typed embedding of miniKanren into Haskell. Our aim was to empower the functional conversion. And after the last brilliant talk, I feel a little bit embarrassed because this is like a baby version of what Santiago has just said. So don't be very, don't expect too much. I'll start from the very beginning, from talking about functional conversion. So in the world without miniKanren, everything is very sad. And for each task, you have to create a program. If you want to find all of the reachable vertices in a graph, you need to write a DFS. But then, if you want to find the path, you need to write a DFS, but with a little bit of the tweaks. And then you want to find all of the paths. And you also need to write some program. And it is exhausting. In the world with miniKanren, you don't have to do all of that. You just write one relation, right? You start with a description of what you're trying to find. You encode it as a relational program. And then you query it in order to find one path, find all paths, find all of the reachable vertices, and stuff like that. And this is really brilliant. And this is something that we all enjoy, I hope. And it powered this idea of creating solvers from verifiers. Basically, the idea is that it's really easy to create a function or a predicate that checks that some property holds for some data, right? But for example, for isPath, it's just this tiny function which can be really easily translated into a miniKanren and then run whatever. And it's much more complicated to find the data that makes the verifier ticks, right? And we don't really want to do that. We want to use miniKanren and all that we have in our power to avoid writing solvers ourselves. Thankfully, it exists. It allows us to view a program as both verifier and a solver. And we, of course, can have compilers and decompilers, evaluation and program generation, like type checking and type inheritance duality, all empowered by miniKanren. And what is the issue with that? Of course, the issue is that it times out very fast. There are a lot of reasons why it happens. And in our research, we focused on the two aspects. The first one is the unifications are expensive, and the second one is that the order in which goals come in the conjunction is very finicky, and it really depends on the direction you want to run your program in. Of course, there are some ways to help with that, and for us, it is a specialization. Specialization is a general approach of creating programs which run faster based on some data that is known statically. For example, if you have a function that implements a power function, and then you know that in your program you only compute power base 5, then you can specialize that program. In some cases, you can do this automatically. Like this general approach was created many years ago, and the idea is just to generate the program that runs on the same dynamic unknown statically data as the previous one, generating the same outputs. In miniKanren, we of course have this same idea, where sometimes we know some arguments. For example, here in the forward direction, we know two vertices between which we search for paths. In this case, we generate vertices which surface beginning and the end of the path, and we run in the backwards direction. But in some cases, we don't know the values of our arguments. We only know the direction in which this program is going to be run. For example, in this case, we know that A will come from somewhere, and we know only that. And we can use this direction information in order to specify the program and make it run a little bit faster. This can be seen in some examples. For example, here we have a sorter relation that sorts a list and function as a sorter in one direction and as a generator of all of the permutations in the other direction. Unfortunately, there is no way to write this program in such a way that it works in both directions. We can only reorder the last two goals based on the known direction that we want it to run. And this is something that specialization for miniKanren is doing. It really, like, knowing something about the mode, it reorders the conjunctions in a way that makes sense, hopefully. And even that is not enough in the majority of cases. As I said, unifications are expensive, and getting rid of as many unifications as possible is one way to fix this problem. So what we did, we created the functional conversion, which takes a relation, and then it basically compiles it into a function that gets rid of all of the unifications that exist there. So it takes care of this knowing the direction. So specialization, in the end, we decided to use specialization only for known arguments, but the direction is encompassed in the functional conversion. In our implementation, we dump our functions into Haskell or Camel or whatever else functional language you want. But I'm going to be talking about Haskell because Haskell is the best, right? All right, so let me go through some examples. This is an example of an addition relation that runs in the backwards direction. So we give our program a sum, and then we expect it to create a factorization into summands. This direction is non-deterministic. When you have non-determinism, you cannot easily provide a function that generates the result, because functions are inherently deterministic, right? So what we do, we instead use streams to express this non-determinism. These streams are something that is like the base pillar of our of any miniKanren relation, and this is something that survives our functional conversion. This is a part of miniKanren that we preserve. So, not going into too much details, we can see that our functional conversion works as it converts every disjunct within our programs into like a stream, and then it concatenates them with M+. So the first case, of course, provides that x is always 0, and z is whatever y is, right? So we returned it as a result. In the second conjunction, we need to do this recursive call, and then we return the result of it. And z is unified here with successor of some value, and this is translated into a pattern match. So basically what we are doing is we classify every single unification in our program into either equality check, pattern match, or a constructor applied to something. And there is, of course, a fourth component, right? What if we cannot classify it into either of these three things? What if we unify two logical variables? This can be exemplified by this direction, where we have only the first argument known in the addition. And here we generate the infinite stream of values, right? How do we represent it? In miniKanren, you use this underscore dot something to represent a logical value, but our goal was to get rid of that at all, completely. Logical variables is something that shouldn't exist in functional programs because functional world doesn't know how to deal with it, right? So as a solution to this, we provided the idea of generators. A generator creates a stream of all possible values that your variable can take, being like a free logical variable. And then we use it to generate our streams of results. And this functional conversion was implemented. It worked somewhat decently, but the issue was that it was implemented over a deep embedding of miniKanren into Haskell, which didn't know, which basically like started with a parser, constructed an abstract syntax tree, and then did all of the steps of functional conversion, which doesn't really matter right now. But the thing is that our untyped deep embedding was terrible. It didn't have any information about types. We didn't have any data type definitions. We just knew that constructors started with an uppercase letter. We didn't have any static checks. We couldn't even check that a given relation was implemented somewhere in the program. It was impossible to extend this language completely. So it was a pain to work on the functional conversion over this embedding. As one of the very clear issues with it came these following two problems. So the first one is, since we didn't know anything about the types of the variables, we could only create a monolithic term type to represent values. Because if you don't know the information, where can you get it, right? And this monolithic term type, of course, suboptimal, to say the least. You could create stuff which doesn't make any sense, for example, as of nil and stuff like that. And you'd be surprised how easy it was to shoot yourself in the foot having this crutch instead of the normal types. The second thing was, since we didn't know anything about the type a variable had, we couldn't figure out what generator to use. And in this case, we just decided that the user is smart enough, they will figure it out. They will figure it out, but it will take them a lot of time. And one crucial thing is that we implemented all of that in Haskell, and we just threw away every single positive aspect of Haskell that exists there, right? We didn't use any information about types. We didn't use any of the static checks that it provides. So instead, what we tried to do next is to create a typed shallow embedding, right? And the requirements to it were threefold. So first of all, we needed typed terms to get rid of that monolithic term type and to empower the implicit generator passing. Secondly, we wanted it to be shallow in order to adhere to one of the miniKanren core principles, namely to be able to extend the language itself. And also we wanted to take advantage of the Haskell type system as much as possible. We also wanted to have access to the AST. So we wanted to be able to reorder conjuncts. We wanted to inspect unification, to figure out where we have values, where we have variables, where we have something partially defined. And also we wanted to have access to relation names and variables. Of course, there are multiple ways to do that. And there are at least 3 types Haskell embeddings that I know of, but now at least. When we first started, we just couldn't make it work with our functional conversion specialization pipelines. So we decided to do our own. Our own is not as beautiful as the Walrus's one, unfortunately, but it looks like this. It also has the disjunction implemented as a sum of some conjuncts. Conjuncts are basically expressed with do notation and stuff like that. We have some small inconveniences, such as we want to create a name for our relation. We want to explicitly say that we are calling the relation, but it is a tiny inconvenience compared to the amount of good we got out of this embedding. How we did that? We started with the logic term type, which is very similar to what Santiago presented, where we have a type with holes in it that represent the logic variables. This, of course, is generated. In the end, it seems like a lot of boilerplate to generate logic term types, which we got rid of by using template Haskell. But this is the easy part. More hard part was to create the shallow embedding itself. And what we did is to use final tagless style. So if you're unfamiliar with it or if you've forgotten, this is the idea of representing your program without an AST, and every single evaluation, the semantics that you give into a program is given by implementation of instances of some type class that encodes the structure of your term tree. And what is nice about that is that you can easily extend it by implementing new type classes with new instances and get all of the beauty of Haskell into your EDSL. So the basic type class that exists in our embedding is the Kanren type class. It looks more or less like this. We can see that there is only 3 parts to our core language. So it's the unification, calling of relations, and fresh introduction of new variables. And disjunction and conjunction come from additional context. So disjunction is represented as a sum from alternative, and conjunction is represented by the applicative. And you may be confused, why applicative? It's monad everywhere, right? But the thing is, we wanted to be able to reorder conjuncts. And how would you reorder conjuncts in a monadic style? You cannot. So what we did, we switched to applicative. And the thing that you saw before that with do notation, we actually used applicative do. So don't be fooled about that. But it doesn't really influence the way that the programmer uses miniKanren, which is really fun for us. As a proof of concept that it works, we implemented several interpreters. So the first one was the normal evaluator for miniKanren, which took us a while, and we had to rewrite our implementation multiple times. But then the complicated part started when we started to work towards the functional conversion. We tried to do the functional conversion, the whole functional conversion over this representation. It didn't really work. So instead, we dumped our representation into a normalized AST, and then we powered the functional conversion from it. Normalization itself was hard enough, and you can find the implementation details in our repository if you want. But what we did in the end is replaced this first block of string parser to AST with an embedded program in Haskell through normalization into AST, and then we dump it into the previous pipeline, generating functions in the end. Just to showcase how the functional conversion results changed after that. So here's an excerpt of a project that balances some tree. Doesn't really matter what it does, but you can see the monolithic type here, which is ugly. And you also see that we have to thread these 2 generators here. And this generator is not even used in the balance program. Instead, it is used in a depth relation, which you just have to thread all the generators through it. And it is really easy to screw it up, mix the order or something. And this all went away when we went to the embedded DSL route. Now we have separate types for separate types for separate values. We don't have any generation. Generation is implicitly computed. It's basically Haskell compiler finds a proper generator among those that exist based on the type of the variable, and we don't really have to deal with it anymore. All right, I think that is it from my part. There is an implementation, there is of course a paper. Check it out, play with it if you want, and reach out to me or Igor with your questions or concerns. All right, thank you.
All right, we got time for some questions.
Can you hear me? Yeah.
This is great, and I understand how this will make it so much faster if you remove the unifications. What I don't understand is how you put it back. So if I have a function that does addition, and now I do the functionalization, do I use that back into my relation? Does it dynamically send me to the right function?
There is no going back from the function to from a function to a relational program. So there is a converter which can be run over the function to create a relational program, and then we deal only with the relational program, and then we like transform it back into a function that works in the direction we want, basically. And this is like a one-way street.
Thank you. As far as I understood, you're dealing with generators, and this generator can produce infinite number of results, right? And then these generators can be combined as a result of functional conversion, so you have a composition of these generators, potentially.
Okay. Okay.
My question is if this composition preserves the completeness.
As long as the generator is a stream, it should work fine, right? Because the stream is the...
Interleaving.
Huh?
Interleaving.
Yeah, interleaving stream, of course. This is the stream which is just from miniKanren. It's stolen from miniKanren completely. This is the same thing that we will use in the interpreter of miniKanren. Yeah.
Okay, thank you.
This sounds like a hack, but it works. Yeah, because like the first iteration of these generators was using lists, and of course when you have lists, it doesn't work. It preserves the completeness. And this is why we preserve these streams in the function, even though they seem foreign.
Can you say anything about the performance differences that you found in using modes?
What we found, let me say this thing. So basically, what we generate in the end is the function that is the same as the previous one, right? We just got rid of some of the small things that we have to deal with manually. So the performance didn't improve by using this typed embedding, as opposed to like the deep embedding and the functional conversion. Functional conversion itself improves the behavior of the programs somewhat. Yeah.
Can you go to the slide with where you changed your parsing to a normalizing parser? I missed a step here. There's normalization going on both before and after the AST. What did I miss?
This is not you who missed something, this is I who missed something. I just wanted to show like the big beautiful picture when only one block changes, but I should have changed two, right? Sorry about that.
No, I got to ask the question. That fully resolved.
I mean, we can dump it into a normal AST, the old AST before normalization, but it doesn't make any sense. We just combined them together as an exercise, actually.
And I have another question. Where are you sending him to grad school?
Sorry?
Where are you sending Igor to grad school?
Oh, this is a good question.
You can't turn that back on me. All right, let's thank our speaker one more time.
This works.
Hot mic.
Try speaking it.
Interesting. All right.
That's new to me too.
All right. Can everybody hear me? Yes. But people can't see my slides yet. Come on. How do I get you to stop? Displays.
Yeah, try doing the
Extended
extended.
display.
Oh, there we go. You got it.
Yes, but now I can't see anything. No, I didn't want extended display. Mirror everything, please. Mirror?
Yeah, try that.
Aha! Now I can see myself. Okay, great. No, don't play. All right, hello. My name is Michael Arantinius, and I'm here to talk about fair intersection of seekable iterators. This is an implementation-y talk. So there's relational programming is a broad tent. I like to think of it as having two sides. There's not a hard and fast distinction between these two sides. But there's the logic side, and there's the database side. And logic programming, we're interested in disjunctively searching a large space of things, maybe an infinite space, and our solutions are going to be very sparse. We might not expect to find all of them. We really care about finding like 1 or maybe 10, maybe 100, but not all of them, sometimes. And we often use top-down goal-directed search for this sort of thing. miniKanren belongs on this side, pretty much. Although semi-miniKanren, maybe not, maybe on the other side. In databases, we care more about conjunction than disjunction. We have a bunch of different constraints, a bunch of different tables. We're trying to intersect or interjoin them all. All of our data is finite. We've got dense, lots of stuff represented all compactly in a table. We want to find all the solutions. And we generally use bottom-up approaches to do this. So this talk is going to be mostly on the right-hand side, but it's going to be inspired by the left-hand side. So it's going to be about conjunction, about intersection, but it's going to show how taking an idea from miniKanren's fair, complete, disjunctive search and applying it over on intersecting search is going to give us an increase in efficiency. So first I'm going to talk about union and disjunctive search. So we can think of logic programming as producing streams of solutions, and our stream might be nil or cons, lazy here. And one way to combine two streams is to append them. This is what Prolog does. It does depth-first search, so it finds all the things in the left. If you've got a disjunction, it finds all the things on the left, and then it finds all the things on the right. And this is not a complete search strategy, because what if there are infinitely many things on the left? So if I take the primes and I append some other stream to that, I'm never going to see 6. All right. And if at any point during this talk you get confused, pipe up immediately. Ask me questions. I like questions. If I can't answer the question immediately, I will punt it to the end. But if you're confused, ask a question. So you might think, okay, I can fix this problem. I'll interleave the streams. I want everybody to take like 10 seconds to think, is this a complete search strategy? And I'm going to ask you to raise your hand one way or another, and I want every hand to go up one way or the other. Don't think too hard, 10 seconds. Okay, time's up. Hands up who thinks this is complete. All right, hands up who thinks this is incomplete. Okay, I'm glad to see so many people raise their hands. Everybody who raised their hand is correct. First, I'm going to show you how it's incomplete. Here's the primes again. Now let's filter that down to just the even primes. So that's just 2, right? But what will we actually get? We'll get, 2's in there, and then we'll get this thing I've notated bottom. What that means is infinite loop, right? It's like, okay, I know the first thing is even, but 3, I don't know about that. 5, I don't know about that. 7, I don't know about that. And it keeps going on like that forever. So as soon as you look at bottom, you have lost. As soon as you try to inspect what's in it, you're stuck. Okay, so let's now interleave the even primes with, cons 3, cons 4, nil. We grab the first even prime, 2, good. We grab the first thing off of cons 3, 4, good. We try to grab the second thing out of even primes, we've touched bottom. We've lost. So if you have bottom, this is not a complete search strategy. But that's not surprising. If you have bottom, there is no complete search strategy. As soon as you touch bottom, you've lost, because you've blocked on one of the things that you were trying to union, and you'll never go back and look at the other one. So we have to avoid bottom. But we can't. If we want to have filter, and this is our type of stream, we're screwed. What we have to do is have a different type of stream that allows us to never generate bottom. So this is what miniKanren does. I was introduced to this through the microKanren paper, but I understand it's pretty standard. Here I'm adding a constructor to my stream type called later. I think microKanren calls these immature streams, and I think I've heard Wilbert call them incompletes. And it basically just says, look, I've computed for a while and I didn't find anything. If you want to go off and look at some other stream, now's your chance. Right? It gives no further information. It just says, I don't want to get stuck. I don't want to be bottom, so here's later. And then we have to make sure that all of our constructors do at most, all of our functions over these streams do at most finitely much work before they produce a later. And all of our functions have to preserve this property. So now we need to take filter. The first two cases for filter are completely standard. The last case just says filter, ignores laters. It propagates laters onward. Union uses this property that we've established. Later acts as a signal to go look somewhere else, right? It acts like append on nil and cons. But when it sees a later, it says, aha, my left stream has done a certain amount of work. I'm going to go switch to my right stream and let it do a certain amount of work. And now, if we define primes in the right way, so primes is infinite, so we have to sprinkle laters through it so that we don't only see a finite amount of work between laters. Doesn't matter exactly how frequently we put them in there, but they have to be in there. If we take primes and we interleave it with cons 3, cons 4, we're going to see cons 2, later, cons 3, cons 4, later, 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 later. And instead of bottom, we just get an infinite stream of laters. Yeah?
So it's crucial that you swap y's and x's, that you're calling union y flexes there instead of union x's y's.
Correct. Okay. It is crucial. Up here, it kind of doesn't matter, right? In the cons case, it doesn't matter, but in the later case, we absolutely have to swap. Okay. Now I want to take that idea. What was the idea? The idea, I claim, was that we wanted to bound how much work we were doing before we started looking somewhere else. We didn't want to block waiting for something to figure something out that could take an unbounded amount of time. We had to bound how much work we're doing before we start looking somewhere else. Now we're going to do intersection. In particular, we're in a database. We're going to assume that the things we're intersecting are sorted arrays. We're going to have sorted arrays of all our data. All of our data is finite. If I have two sorted arrays, how do I find the intersection? How do I find the things that are in both arrays? Here's one way. Look at the first thing in each array. If they're equal, well, there's one. Emit it and move on. If they're not equal, take the bigger one. So here this is 6. Search for the bigger one in the other array. Search forward. So in this case, we immediately hit, can people see my cursor? Yes, excellent. We hit 9, right? Easy. Okay, 9's bigger than 6, so search for 9 over in array B. It's not 7, it's not 8, 20. Okay, that's big enough. 20 is bigger than 9, search for 20 over in array 3, 11, 12, 15, 17, 21. Okay, go search for 21 in the other one, because 21 isn't 20. Okay, there we find it. This works. The problem is this bit where I search linearly through each thing. If the next element is close to the front, this is fine. But the next element that's bigger than 20, right? We had to go through a few numbers. That could have been 1,000,000 elements, right? This is an array. We have random access. We can do better than just linear scanning. Binary search, for example. The problem with binary search is the best case is log n, the worst case is log n. With linear scan, if it's near the front, we get there really fast. But if it's far away, it takes a long time. With binary search, it always takes a logarithmic time. You can hybridize these. You can do exponential search, where I look at the first thing, second thing, fourth thing, eighth thing. I keep on jumping further ahead, and then once I've got an interval, I binary search it. This is nice and adaptive. If it's nearby, I find it fast. If it's far away, it takes logarithmic time. The details of this kind of don't matter. The point is, we can do these searches efficiently. And if we do these searches efficiently, then this intersection algorithm is efficient. Okay. What did I need in order to do this intersection algorithm? What interface did I use? I used the ability to efficiently seek forward in one of my inputs. And that's it. So if I have this method, that seeks forward an iterator to the next thing satisfying a condition, then I can write an intersection. In fact, I can do one better. The intersection of two seekable iterators is itself seekable. If I want to seek in the intersection of two iterators, I seek in the first one to satisfy the condition. Now I've got some x that satisfies the condition. I seek in the second one for the next bigger thing, seek in the first one for the next bigger thing. I just do that back and forth that I showed you on the previous slide. And then once they're equal, I've found something in the intersection. So this is very nice. It means that intersection is compositional. I can write over these seekable iterators. If I want to intersect three things, for instance, I can take the intersection of x's and y's and intersect it with z's. Does anybody see a problem with this? It's not an obvious problem. Perhaps an example will help. Here are three relations, three sets. There's the even numbers from 0 to 1,000,000, there's the odd numbers from 0 to 1,000,000, and there's the endpoints, 0 and 1,000,000. The intersection of all of these three things is empty, of course. There are no even odd numbers. If I intersect evens with odds, and then I seek in it, what happens? Well, 1 is bigger than 0, so look for the thing bigger than 1, which is 2. So look for the next odd bigger than 2, which is 3. So look for the next thing bigger than 3, which is 4. It ping-pongs back and forth, and it hits every single element in both evens and odds. And that's fine. We can't really do better than that without having the special insight that one of these is the evens and the others is odds, right? What happens if I intersect odds with ends? It goes real fast, right? 1 is bigger than 0, so I search for the next thing bigger than 1 in ends, and it's 1,000,000. So I search for the next thing bigger than ends in odds, and my exponential search very quickly runs off the end of the array. Logarithmic time, and I know that this is empty. Okay. I told you I could do this compositionally. There's two ways to do this compositionally, depending on which two things I intersect first. But if I intersect evens and odds first, then if I seek in this whole intersection, the first thing it does, right, is it seeks in the left thing. The left thing is intersect evens odds, and we just saw that that is super slow. It takes 1,000,000 units of work. But if I do it the other way around, it looks in evens, and then it looks in odds and ends, and it very quickly says, okay, I'm done. So the interface looks compositional, but the performance is not. Performance is crap, depending on how you do it, which is very annoying. You don't want your user to have to think about this. It would be nice if it just worked. Why is it not just working? Well, it's because I claim this interface doesn't let us do a fair intersection, right? We're blocking. When we take the intersection, and the left thing is an intersection, we wait for it to produce an element, which could take a lot of work. Not an infinite amount of work. These things are all finite. But we're in database land now, and linear work might as well be infinite. We don't want to do that. We don't want to take a linear amount of work. We'd much rather do this. We'd rather visit x's once, visit y's once, visit z's once, do a logarithmic amount of work for each one. But how can we do that? Well, we take the same insight. We allow ourselves not to produce a result. Yet. So instead of saying, I'm going to find the next element satisfying the condition, I'm going to find something, and I'm going to tell you whether it's actually in the intersection or not. I'm going to tell you whether I have found something. So here I'm going to return a Boolean flag found and an x, and x will always satisfy the condition. All of the remaining elements will be at least x. And if found is true, then x is actually one of my results. If found is false, x is just a lower bound. It's just saying, I did some work, and here's how far I got. I know that I don't know what the next element is, but I know whatever it is, it's bigger than x. And so then it's really easy to seek in the intersection of these things. I seek, yeah?
Sorry, what's the difference between x satisfies cond and x is yielded by the iterator?
So, x is just some value. When I say yielded by the iterator, I mean it's in the sequence, in the set that the iterator represents. So remember, one of the things we're interested in is the intersection of two sets, right? So Found is going to be true if it's in the intersection when I ask the iterator for that. If found is false, all x is a lower bound. All it is a promise that the next element is at least x.
So x could be some default value that satisfies.
In principle, but it has to satisfy cond.
Yeah.
Yeah. Right? In fact, what x is going to be is it's going to come out of one of those things that we're intersecting. It's going to say, I was searching, I got up to here. I don't know that this value is actually in the intersection, but I know that anything in the intersection is bigger than this.
Okay. So x might not even be in the set that you're searching.
Yes, exactly. That's the point, right?
High watermark so far.
Yeah, it's the high watermark so far, right? If we go back here, right, if we interrupt this search in the middle, right, when we get to 20, 20 isn't in the intersection. But I do know that whatever is in the intersection next, it's bigger than 20. Yeah. Yeah.
Quick question.
Yeah.
When you have done the intersection of x's and y's, and you return an x, is that x in the intersection of x's and y's?
Well, what do you mean? Like that's exactly what I'm saying here, right? When you seek in the intersection, it'll produce found in x, and if found is true, then x is in the intersection.
And found is false?
Then it might not be.
Is it a member of x's? Or guaranteed to be either a member of x's or a member of y's?
In the case of intersection, it's going to be one of theirs, yes. Is that guaranteed? No, we don't need that. We only need that it's a lower bound. I don't know how you'd come up with it, because this code is supposed to be very generic. So how would you get your hands on an x except through one of them? But who cares? Once we have a lower bound, we have a lower bound. So here's how you seek in the intersection of a and b now, and this actually has gotten simpler. I seek in the left thing for the condition that you want. Now I seek in the right thing for something bigger than the x I got out. When have I found something in the intersection? Well, if I found it in the left thing, and I found it in the right thing, and they're the same thing, then I found an element of the intersection. So I return. And the key point is I return after having done one call to each of my sub-iterators. So I'm bounding my work. Each one of them only gets a single call to do its work. So if I compose things together, the call is going to look like donk, 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 donk. It's just going to iterate through my tree once. None of this twirly-whirly stuff. All right. Is this clear? Okay. How do I actually get out all of the elements of an iterator now? Because I've made that more complicated. Previously, whenever I seeked, I would get an element. Now, I have to put the loop at the top level. So previously, there was a loop at every little level that went twirly-whirly-whirly until it found something. Now I have to put that loop all the way at the outermost level until I find something. And so I do something like this. To exhaust an iterator, I keep track of whether I found something and what that thing might be, and I keep looping over. If I found it, yield it, and then seek for the next greater thing, strictly greater, and otherwise just keep on seeking for something that satisfies that bound. Yeah?
I guess the point is exhaust is not compositional in the way that the iterators are.
Yeah. Exhaust goes all the way at the top. This is for converting a seekable iterator into a plain old list of things. So, how far does this idea go? I am not going to give a full explanation, but I claim it can go all the way to relational algebra. So we have intersection. If we have a relational join, foo of xy and bar of yz, we can do this as sort of nested intersections and loops, right? So in this case, there's really only one join variable. I pick an order over the variables that I'm going to solve them in. I'm going to find a value for x that might be possible, and then for that value, I'm going to find a value for y, and then I'm going to find a value for z. So I'm going to look for each x where there is a chunk of foo. Remember, foo's in some sorted order, right? So I can iterate over the chunks which have the same x value pretty easily, right? Then once I fix an x value, I'm going to do an intersection between that chunk of foo, which has some y values, and bar, which has some y values. And then once I found a candidate y, I'm going to look for every z in bar for that y. And this is called a trie-join, because you can think of these as sort of being tries, right? Foo is a trie that has a level for x's, and then within that a level for y's. And bar is a trie that has a level for y's, and then a level for z's. And if you use our leapfrog intersection plus this trie-join, you get leapfrog trie-join, which was the algorithm that I started thinking about and that I came up with this based on. So you can do relational joins. You can do unions. This is not that hard. It's like the merge step in merge sort, except that you have to adjust it to be seekable. I think you can even do existential projections, because then what I'm really doing is I have a bunch of seekable iterators, all of which I need to merge together. So it's a big, wide merge. And you can use a priority queue to do this. You just keep it in a priority queue sorted by what the lowest key is. So the project this came out of is me trying to implement a little data log engine, right? A little data log engine in Rust with this, sort of embedding of iterators, using iterators, these seekable iterators for everything. And I also wanted to do weighted programming, because why not? If you make your things key value sorted arrays, this is really not that hard. You just have to make sure to combine the values in the right way. So far, I have a bunch of runtime stuff and no front end. Actually, writing queries in this language sucks. You have to know exactly what you're doing. So actually, how much time do I have? 10 minutes. Okay, that's enough time. Where is? All right, that is. Right. Here is a little triangle query in Dijkstralog, or in like the Rust library. How readable is this code? Okay. This is like, I define my three relations. They're tiny little things. There's tiny little sorted vectors. I once fucked up sorting them by hand, so I put in some asserts. You get wrong results, as it turns out, if they're not sorted. Okay. This is turning these into nested iterators using my library. So like, just to look at one of them, whoops, let's make that read only. Like, find me the ranges of this R relation on the first variable in it. Okay, within each of those ranges, give me an iterator that maps over the ranges on the second component, right? And you do these to each of these to turn these from sorted vectors into nested iterators. Ignore those lines, they're not important. Important lines are these lines, right? Here I do a bunch of nested intersections on iterators. I intersect R and T on, so the query I'm running here is this, R of AB and S of BC and T of AC, right? So R and T share the A variable, so I join them, and then I map over that, and I get a chunk of R on the B's and a chunk of T on the C's. I join the chunk of R on the B's with S, which has the B variable in front, and then I join the chunk of S that's on the C's and the chunk of T that's on the C's, and with the values I multiply them all together, because why not, right? And in this way I compute triangles. And it goes reasonably fast. This needs to be bigger, doesn't it? Right? So I'm going to load 10 million edges from a little social network data set and run my triangle query and find how many triangles there are. Here we go. Yeah, about 6.5 seconds. I also have transitive closure. You have to feed that a much smaller amount of data because it's materializing the entire transitive closure, and that's big. No, I do not want 10 million. That's way too big. Okay, this is going to produce a lot of output. But in particular, this is going to deal with 240,000 edges. Boop. Took a bunch of iterations. Yeah, it took 9 seconds. Yeah. And you have to implement an interesting data structure because you need to actually be able to read and write from your data structure in order to do this, because you're repeatedly merging more things. So I needed an LSM data structure, not just sorted vectors, so that I could write into it and still query over it. So Oh, out of, it's some Stanford Snap data set. So it's, this one is on the live, no, hold on. Some citation network. Yeah. So, right, where is, yeah. That's the paper link. I should note that this idea, I came up with it, and then my advisor pointed out, hold on, people have had this idea before. And these are the people who've had the idea before. They phrase it pretty differently, but they're working in the tensor algebra space. Surprise, surprise. So yeah, go read their paper. And, oops, is that the end? Yeah, that's the end. I think, oops, why can't I escape? I think, to the extent that I have takeaways, logic and database programming have some things to learn from each other. It was surprisingly fun to take this idea from microKanren and like apply it and actually get something useful out that runs reasonably fast. Part of the point of declarative programming for me is that the user shouldn't have to think so hard. It would be nice to find ways to make order matter less. We've already seen some ways in which order of conjunction seems to matter an awful lot. That's kind of a pain in the ass. Yeah, I'd like to think about how to make that less of a pain in the ass. And like, this seems to be a form of fair conjunction, but it's like only for database style stuff, right? So it's not immediately obvious how to apply it in a Kanren setting. Willibird told me that there's a prologue that sort of does this called Andorra Prologue, and I never had time to look into it, and now I really want to look into it because it seems like you ought to have some form of fair conjunction where you don't, at least don't starve if you put your conjuncts in the wrong order. But that's all future work, I suppose. All right, thank you.
All right, we got time for some questions.
Thanks, this was a really great talk. At least the image that you showed earlier of how the associativity technically holds but fails to be performant reminds me a lot of the reflection without remorse technique, in which something like difference lists are used in order to make append associative, the associativity of append performant. And I think there probably is a generalization here where you might think of, oh, the later element of, I guess the ability to say, hey, I'm not done yet, but here is, I've done some amount of work. You could probably make some connection to a continuation there where you say, instead of this is, the element you give is, here's where I left off. And so you might say that's like an arrayified version of what would be more generally considered a continuation. So I guess the question then arises, do you think that this could also be improved by the methods that are done in the Reflection Without Remorse paper where they kind of use a more general data structure underneath?
I'm not so familiar with Reflection Without Remorse, so I would be interested in looking into that. Maybe we should talk. I will say your question made me think, like, I've presented this as a sort of imperative interface that mutates the iterator. But in the actual paper or the abstract that I submitted, I do it in Haskell without mutating anything. So, and there's explicitly sort of like a function that you call when you want to search the rest of the sequence. So it looks even more like a continuation. But yeah, maybe we should talk about this Reflection Without Remorse.
So you mentioned that this is a little bit difficult to use.
Yeah.
And my question is sort of two sides to it. One is, what specifically makes it difficult to use? And the other side is, if you were to have a full front-end language that was compiling back to this library, is it of the nature where the front-end language could be easy to use, it's just the compiler has to figure out all the technical details to get it to work into your library? Or is it more fundamental than that, where a front-end language would not be able to address that problem?
I think a compiler could totally target this language. You need to work out some details, but that's the direction that I hope to go, or at least to, I don't know, maybe throw some macros on it. I don't know whether I want to go all the way to a compiler.
With such a compiler, would the front-end language have the same difficulties in use that you currently have?
No. The front-end language would look like Datalog. Yeah.
Okay,
Yep.
I wasn't sure if you were done. This is very interesting. Maybe I'm missing something, but if you can go back to maybe the one before this, I think. Maybe the one before this. Okay, and maybe I'll say this.
What was the slide about?
Right. So I'm kind of curious if you've thought at all about like metaprogramming applications to this. The reason and the reason I'm saying is obviously this is all sort of in the abstract domain. You haven't given us any implementation or code, but in some sense, it would be nice to, on the fly, be able to make a flat intersection algorithm. And I'm wondering if there would be any difference in performance. Instead of, I mean, what you did is kind of doing that, but it's still having the nested intersection structure, right? And I would be curious to know if there's any differences that would come up if you were able to take however many queries you want and lift them all to the same level in a sort of metaprogramming way.
I mean, sort of the point of this approach is that you don't have to do the metaprogramming. If you have the metaprogramming, if you're in a query compiler, you can just flatten everything out. And then you don't even need to have this weird iterator structure. You just do the n-way intersection. The hope is that modern compilers, like Rust, are smart enough and do enough inlining and enough optimization that they will get rid of all the overhead that might, the sort of constant overhead that might occur because I've nested things. They seem to be smart enough to produce reasonably fast code. Do they get rid of all the overhead? I don't know. Certainly, I've tried handwriting an intersection loop, and it's like 2 or 3 times as fast as these things. So there's definitely some performance left on the table.
All right, let's take one last question.
Hi, thank you for the talk. I just wanted to ask, have you heard of synchrony iterators? It's,
no.
It's like very similar to this, except I think you are generalizing and introducing the notion of fairness. I just wanted to maybe suggest you can have a look at that, because they somehow allow you to do something like this, but the front end is just a list comprehension syntax, which I thought was pretty cool. So yeah, I think just wanted to point it out. Yeah.
All right, let's thank our speaker one more time.
They borrowed my adapter. This is mine, right? Okay.
Alrighty. Up next, Shengyu is going to tell us about encoding numeric computations and infusing heuristic knowledge using integrity constraints in stable Kanren. Tell me about all of those things.
Okay, thank you, Jason. Good afternoon, everyone. My name is Xiangyu from Arizona State University. This is the topic I'm going to talk about today. Let's get started. So from the beginning, we know the miniKanren shows a natural way to extend functional programming to relational programming. And since then, we have multiple extensions. So for example, miniKanren on the written schema book, it shows a way to use the bitwise relations to encode numeric computation relations. Also, we have cKanren as constraint logic programming to increase the expressiveness. Then we have rKanren, and multiple Kanrens here, to demonstrate a framework to allow guided search by the programmer. Then we have stable Kanren, which extends the miniKanren with negations and the integrity constraint under stable model semantics. So more specifically, this is the operator have in the very minimal version of the miniKanren. Have the unification, fresh, and conti. Then for stable Karen, add 3 more operators. It's a notto for negation, to define to unify the goals, and a constraint to input the integrity constraints. Okay, now we have all these operators. Now the question comes into how we use the about constructors to write the pneumatic constraints in stable Karen, just like what we did in the reason schema to have the numeric relations. And just like the C Karens can perform some numeric computations. We also want to know how to infuse heuristic knowledge into stable Karen so that just like the CLP constraints used in C Karen and the R Karen has the guided search. So here we use the Send More Money as an example to go through this project. Now we all know the foundation of relational programming is just all about symbols, okay? Then the symbols and the logic variables are unified through the unification and the resolution. So for example, we can unify the logic variable x with cat, it's a seed. Then we'll try to do x unify with cat, then unify with dog. First we successfully unify the x bounded to cat, now later we try to bound it with cat, dog, it gives us a failure. So this way we turn unidirectional functions into the bidirectional relations. So we already see a lot of examples about like running one program back and forth, forward, backward. Examples have not spent too much time on this. So here like symbols, it can be anything. So for example, cat and dog, some emojis, numbers like 6, 7, and 42. So when it comes to numbers, then we actually have more computations than just unifications, okay? So here is a side-by-side comparison. So for example, in the relational programming or logic programming, we have the unifications on the left-hand side. Then in the mathematics, it's just the equation, okay? So we can say, okay, symbol is symbol 2, is unified with the other symbol 2, or maybe we call it number, it's a seed. Then 2 and 2, are those 2 number equal? Yes, true. And same thing for like 2, 3, is the case. Now, how about we have the numeric computations? For example, right now, if we have operators like plus and minus to use with like equation or we call it unifications, okay? 3 plus 2 equals 5. So this is the math definition, is true. How about 3 is symbol plus symbol 2 unified with 5? This will be failed under the unification algorithm because it's like on the left side we have 3 symbols, 3 plus and 2. It's definitely not the same as the symbol on the right-hand side. So adding numerics computation to this relational language is not quite straightforward. And it's mainly one of the reasons like, okay, CPU is unidirectional. Computing numbers as a function like take input, produce output. If we have the relational CPU, okay, we're happy now. Hardware people things. Now, so since we don't have this relational CPU, there are 3 approaches to support numeric computations. The first one, let's build a relational CPU. Second one, we're converting things into symbols. Third one, we're creating a constraint store. So first thing, like we're building a relational CPU is basically, okay, we have turning functions, computing hardware into a relational things, right? Then converting into a symbols is like, okay, we perform the numeric computation and then convert the result into a symbol. Then the third one corresponding to, okay, now how about we impose the numeric computation as constraints on the variables and the symbols. Now we're back to like, okay, the simple things like, see, only the unification and the equation, and no more other operators we needed. So some related work. First, let's build a relational CPU. It's actually mentioned on the reason schema books. So it proposed the bitwise relations to simulate a relational CPU. We need to represent the numbers. So all the numbers are represented as the list of the reversed binary bits. For example, the 19 will have the representation like 11001. So this is called the reversed binary bits because the first element is actually the lowest bits. So from here, like we can have the unidirection. We can turn the unidirection functions XOR into the bidirectional relations XOR. Similar to the relations we can define for the endo, and we use XOR and endo to build a half adder and a full adder, just like we learned from the computer architecture how we build a modern CPU in the same manners. So this is one of the example definition of the XOR on the reason schema books. So we have like 4 kind of the bit operations combinations together, and based on each one, we have 4 truth tables outcomes. It's encoded everything here. Okay. Now the next approach is like we're converting into symbols. This is the problem we had before, right? 3 symbols plus 2 equals unified with 5. It fail under unification. So one approach Prolog is doing is you introduce these notorious is operators. So we call x is 3 plus 2, then x unified with 5. Now this time it will succeed because the operator is actually performing the numeric computation, doing the plus operations, then convert the result into symbols. Now we can unify the things together. But it comes with the cost. As the downside is like, okay, this operator is impure. This impure operator make the logic programming is no more relational. Okay, so this is one example of the program written in the Prolog. So for example, we have a plus x, y, x, z. We say okay, z1 is the x plus y, then unify these two, z1 and z together. So we can do first, okay, we verify the things 1 plus 2 is 3. Is that right? It's true. Okay. Second one, what's the outcome of 1 plus 2? It's 3, s unified with 3. How about this? 1 plus something is 3. So under these settings, Prolog give us an error. I cannot handle this. Same thing like, okay, what's the 1 plus something equals to something? Prolog still cannot do that. Now comes to the third approach, is we're creating a constraint store. Like I mentioned before, all this numeric computation can be converted to constraints and imposed on the variables or the logic value or the symbols or the variables. So this is the issue we want to tackle. So in constraint logic programming, we impose the numeric computations on variables or symbols as constraints. So in this case, the constraints are maintained internally and evaluated at the end. So this is a new operator they introduced, the pound equal. So x pound equals 3 plus 2, and x unified with 5. In this case, it will support some features we want. So same thing, same program, but we use the CLP operator, pound equal here. First, still returns true. Second one, still s unified with 3. Now we ask like a 1 plus something equals 3 is able to find out, okay, r needs to be unified with 2. And something, 1 plus something is 1 plus r is s. It returns as like, okay, 1 plus r pound equal s. So in this case, like we need to do additional, like specify the domain to it. So for example, CFP FD, we need to say r in some certain range of variables, then s in something, and give you a more detailed result. Same thing for the last examples, like QRS, all variables. Okay, so now there's the variable constraints and integrity constraints. So variable constraint we have seen before in the CLP, it basically allows the numeric constraints on relational variables. Okay, there's the miniKanren uses the CLP scheme to introduce new operators like in to specify the domain, in FD, plus FD, and the not equal FD, etc. in the miniKanren. In addition to variable constraints, there's another options we can do that. It's called integrity constraint. Basically, integrity constraint it controls the outcome of the relational goal. So notice the difference here. One is like we impose the constraint whatever on the variables. This one, we basically checking the goals. SPLASH' introduced this new operator called constrainto. Both approach will enable solving the combinatorial search problems. So on the left-hand side, we have here we use the n-queen problem to identify the make sure the diagonal queens that do not attack each other. So on the left-hand side is the miniKanren's approach. So here, like I said, we basically just still impose all the constraints on these variables, and we will refine these constraints later. On the right-hand side, we have a SPLASH' version of this diagonal check in n-queen's problem. So I will go into this in more detail
from here. Some preliminaries. So behind the stable Kanren approach, basically it's used the generating and the eliminating combinations approach. So this integrity constraints needs to be combined with the negations in normal programs to enable new declarative programs. So here I'm not showing a mathematical definition for normal programs, just to save some time. And so here, the main idea is like, okay, we can generate a combination using the even loops and the negations in these normal programs. And we eliminate the combinations using integrity constraint. So basically, integrity constraint is an odd loops. So here's one examples. We start from the very basic version of propositional logic to have binary choices. So here we have pick. If we pick something, and it's not free. Or if this thing we didn't pick it, it's free, so we didn't pick it, right? So this is the what we call even loops over the negations. So we can only have one thing to be true at a time, either pick or free. And so in this case, we have the binary choices. So extended it a little bit, so we introduce the variables here. It becoming a predicate logic. Now we can have like pick something if it's not being picking, or otherwise it's free if we're not picking it, right? But here is one problem, like, okay, this X, there's no domain. In CLPFD, we have the in keywords to specify the domain for it. So how can we get a domain to this? So we actually getting the domain through the facts. So we can give a bunch of numbers. So for example, we say X is a range of numbers. So we can define multiple numbers. Number can be 1, 2, and 3. And we can have another set of the range, for example, num1, and it specifies 4, 5, 6, or whatever. So this is the flexibility of you can specify the domains. Okay. Now, this is the knowledge we have. Now we move a little bit further, goes to 2D domains. So for 2D, basically we pick X and Y on the chessboard, right? X by Y. So the range, the domain of the X, domain of the Y, we specify here. This is the even loops to generate all the combinations. Now there's a domain, the 8 by 8, so it would be the 8 queens problem. Now we can use the integrity constraint to control the outcome in here. So basically, integrity constraint, as I mentioned before, is odd loops. So odd loop will introduce a contradiction. So here is one example to use the integrity constraint to eliminate the combination to, for example, the 2 queens cannot be placed on the same row. This is one example. So the first line is the headless version. So if so if we pick a queen, for example, 1, 1, and 1, 2, so X will be 1, Y be 1, it is 1, 2. And the whole body of this rule will be true. So it basically is saying like true imply false. So this is the violation. Okay. So there's equivalent version. It's like, okay, we can convert these headless rules to introduce odd loops here. So saying, okay, it's fail, and the body part is not fail. So if all these subgoals here evaluate as true, so here is forming the odd loops. See, this is a contradiction. Okay. So a solver needs to prevent this kind of contradiction happens to find out the proper combination we want. So here is an approach called the CAVE, constraint as verifiers and emitters. So what CAVE does is like, okay, integrity constraint, because we also need to handle the numeric computations in there, right? We didn't talk about this yet. So also those two approach applies here. The first one is like we perform the numeric computation and converting the results into symbols. This in logic programming can call it grounding. So we removed all the variables and into values and created symbols. Then we assign choose value to each one because it's propositional version. Or we impose this numeric computation as constraints on the variables and the symbols through this like a CAVE approach. Okay, so still using the same integrity constraint as the examples. So let's check the first approach, like we do the computation and convert into the symbols. So for make a smaller domains, for example, is a 3 by 3, we will create like 9 symbols from like pick 1, 1, 1, 2, 1, 3, 2, 2, blah, 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 to the pick 1, 3, okay? Or 3, 3, sorry. This one should be 3, 3. So, and all these integrity constraint with the variables, now we remove all the variables, sorry. Need to go back a little bit, so not here. Yeah, all these like variables are removed. Now it's a grounded versions. Okay, then grounding version have the problem like we take out too much memories, right? You have the memory bottlenecks. So that's why like here we have the cave approach. Integrity constraint can be written as the emitter and the verifiers. An emitter is the head of normal program class that emits values. Then once the value emits out, it will be captured by the verifier. Basically, verifier is a Boolean expression that receives values and verify them. So for example, here in the unqueens problem, like, okay, we have 3 emitters, pick, free, and the none, right? Or the head of the class. Now, in the integrity constraint, we can have 2 emitters here, is a pick xy and pick uv, and 2 verifiers, x equals v, or y not equal, x equals u, or y not equals v. So this verifier can form the constraint handlers. And we will show like these things in stable Kanren. So a quick recap. This is the generate and the elimination approach we're gonna do to use in stable Kanren. So Cave help us to implement constrainto to support the integrity constraint in the constraint store. So whatever values we emit out, we collect them and we verify, do the numeric computation, and we terminate the resolutions based on the evaluation result. Okay. So the integrity constraint will break into 2 parts: emitters and the verifiers. This is the syntax of the constrainto. Two brackets left. The blue one is the emitters, pick xy, pick uv, and the orange part is the verifiers. So notice here, like we still can use the even loops and negation to generate all the combinations. So this the program is the straightforward translation from the logic program. Now, stable Kanren will support solving the kind of combinatorial search problems and constraint satisfiability CSP problem using these declarative generate and test paradigms. Now we come to like how to do the numeric computations here. So basically, reducibility shows us that every problem in P or NP can be reduced to this CSP, right? We only need to find how to reduce it. This is how we program it. So we come to the last problem, is how to write these numeric computations under such paradigms. So the key idea, okay, we do the numeric computation as constraints in the verifiers. So this is the verifiers from the previous slides. So we generate all possible combinations, and the symbols are over finite domains. Now the symbols are basically emit from these emitters and will compute as numbers in the verifiers. So same thing here, we have emitters. We only use the pick here right now. So we will show the examples as the arithmetic relations in stable Kanren and send more money in stable Kanren as well. So to define Plaso is a relation, right? We generate all possible combination over the finite domain. So depending on how many numbers you have, you can have 10, 100, thousands, whatever, but we didn't show up the numbers domain here. We just show like, okay, we first using these even loops to create all possible combinations. Does it satisfy the relation plus or not? We don't care. So we create all kind of possible combination among all these 3 numbers. Now we have the emitters to emit the symbols. Then we can do the computation in the verifiers. So in the constrainto, we will say, okay, the Plaso, you emit something. Then in the orange part is verifiers. So we can do the computation. To add them together, if they are not equal to Z, this is the thing we don't want. We want the Plaso to satisfy these constraints, right? Then if it's unPlaso and they add up to be satisfy the constraints, we don't want this to happen, right? The satisfied part should be in the Plaso, right? It's not unPlaso. So similarly, the minus O can be defined using Plaso just by swapping the 2 parameters. And you can also define multiplo and divido. Now come to the send more money examples. So this puzzle requires choosing different single-digit numbers from each letters to satisfy the equation, and no leading zeros are allowed. So to begin with, okay, we do the same thing. We generate all possible combinations. So we have 8 letters. We have 10 digits over these finite domains. Okay, so we can say we have assigned each letters with the values, or we are not assigned this letter with the values, right? So this assign or assign part. Now, this is the additional constraint to make sure, like, okay, each letters will get 1 digit values, and each value does not assign to multiple digits. So this part I will not explain this in too much details. The important part is like, okay, how do we check the equation, like send plus more equals money. So same thing here. We have emitters. We want to do the numeric computation in the verifiers. So in the constraint, first we have like 8 emitters, right? We will assign letter S with some value, E and D or something with some values, right? Then in the verifiers, we do all these kinds of computations. We give each letters a weight. So for example, S give a weight of 1,000, E is 100, N is 10, D is 1. Okay, and converting to the numbers, and we see if they satisfy these equations. Okay, so we run the queries. The query would take like more than an hour to find one answers, which is not ideal for these kinds of small puzzles. Now comes to the second part of this talk. It is like, how can we infuse heuristic knowledge to speed it up? The overview is like, okay, because right now stable Kanrens still use the brute force to perform the BFS. There's no heuristic embedded into it yet. And this search domain size is 2 to the power 8. Okay, so we will gradually apply this kind of guided search techniques to using this technique like query variables reordering, break a big constraint into smaller constraints, identify critical emitters. In this way, we can reduce the solving time to less than 20 seconds. And we also demonstrate a hybrid solving approach that utilize the external Oracle verifier to further reduce the solving times. So let's get started. First one is the variables reordering. So to make it easier, every things run in a query. So for example, this big chunk of box, we just abbreviate as SEND-MORY. So this is the ordering of we run the queries into it. Okay, then if we run the single query, we will have some measurements here. And we notice something like, okay, if the values we are getting is smaller, for example, if you're getting 0 and 1, it basically takes less time because it prunes out the search space pretty fast. So how about we rearrange the variables ordering using this number ordering, like it goes from 0 to 9. So if we change the variable ordering to OMY, ENDRS like this, the query to find one answer only takes around 3 seconds. But the exhaustive search still will take around like 5,000 seconds, which is not quite ideal. So that comes to the second approach. Is like we try to break the big constraints. So previously we had one giant big constraint has like 8 emitters in totals like this. And how can we break down into the smaller constraints like here, each digits, right? So one way to do that is like, okay, we have multiple, this 5 almost finished. Sorry about that. I think I should have 2 more minutes because previously, yeah. So here, like, okay, we break into smaller constraints. Now we will be able to see the performance improves further because smaller constraint actually easier to satisfy and verify. Also, like here, from here, we can identify the critical emitters. Like some emitter, the higher bits actually depending on the lower bits. So we combine with the variables reordering techniques, we can lower the time to find one answer to 0.46. And we can also have like 300 seconds or so to do the exhaustive search. Then the last thing is like, okay, the Oracle verifier. So basically you allow the hybrid solving approach. Like we can apply some like human reasoning techniques to come out with some partial answers. So we can easily figure out M is 1, O is 0, and the S is 9, and encode these things as verifiers, and to send into the solver to kind of guide the solver. Okay, we already have some partial answers. It help us find the rest. So by doing this, the time reduced like 5.17. And if we also like put already known answers beforehand, this improve even further. Okay, some conclusion and the future work. Conclusion here is like we show the numeric computation in stable Kanrens and show the kinematics approach to this. I will fly through it, not really line by line, but you see the highlights here. We can do some like guided search, blah, 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 and allow hybrid solvings. So for future work, definitely like we kind of want like, because right now verifier only checks our outcome. It didn't guide the resolution yet, but as we can see from here, actually whatever things we write down as a verifier can help us to guide the search process. So building optimizers will be much nicer, just like a SQL engines. You can generate the query plan before you run the queries. So we can handle all this kind of the technique we mentioned before in these kind of optimizers. And we also want a generic heuristic algorithms. For example, the top-down conflict-driven things causes all no-good learnings. And we more specifically, when this kind of symbols come to the numbers, whatever technique used in the COP. So, for example, we have an analyzer to figure out, okay, this is basically all numbers. How about we use the COP to improve the solving speed? Then we believe there's no answer for the NP-hard problem, right? If we find things heuristic work for everything, we basically solve the P versus NP problem. Therefore, like we kind of want to allow the user to customize their domain-specific heuristics into it. If they have no idea, we just brute force. Then, yeah, some improvement about like, okay, unsafe arrows seems to support it. That's it. Thank you, guys.
All right. I'm sorry we had to abbreviate the last bit of that, and we don't really have time for questions in this session, but luckily we've got a coffee break. So this would be a good time to continue asking Sheng-Yu about the rest of that work or any questions you might have. We'll be back in, I think, 30 minutes. Cool. All right.
Hello, can you hear us?
Hello, yeah.
Oh, perfect.
Okay, yeah.
Hello, can you hear me?
Yep.
Yeah. Hi, I'm Dmitry. I'm your session chair.
Oh, hi. Nice to hear you.
Thank you. Who from the set of authors will be giving the talk?
I'm Attila Egrinagi.
Okay. Okay. Yeah, I need this information for introduction. I presume we start within 10 minutes.
Okay. Yeah. There's a bit of a delay. Yeah, okay, but that's
So okay. Yeah, the microphone will be handed over.
Is the voice okay?
Yeah, we can hear you clearly.
Okay. Yeah, I have fancier mic, but people complain that it's worse than the MacBook's mic. So
No, everything fine for now. Hello, welcome to the third section. Yeah, I'm just addressing the audience. Welcome to the third session of miniKanren and the Relational Programming Workshop, and we have two talks. In this session, the first one will be streamed live, and Attila Egrinagi will present his joint work on computational exploration of finite semigroupoids. Please, you are all online.
Okay, well, thank you very much, and apologies for not being able to be there in person, but I still try to give you a entertaining talk. So this is a joint work with Christopher Nehanif. I'm from Japan. He's from Canada, and so we are doing computational exploration. So I have to say a few words about that. But what I mean is that we do programming for epistemological purposes. So we want to learn something about an object, and that's why we write programs. So it's just as a note on the current affairs, that's why we are not really interested in AI tools for coding, because we want to understand ourselves. And that's one reason why we are interested in declarative languages for describing mathematical objects. Because that's exactly what we want to talk about. It's like, what are the properties of these objects? And that's, of course, our research is a bit of a self-referential, because we are studying computation by computational tools.
So we are interested in theoretical computer science, automata theory, but algebraically, and that is semigroup theory. And recently we realized that, we have to go to category theory, and we have to do our decomposition algorithms there. So yes, I mentioned semigroupoid, or you can call it semi-category. So what is it? Well, there are several ways to understand that. If you come from category theory, you might say that, it's just a category, except that the identity morphisms are optional. Or if you come from semigroup theory, then you say that, okay, it's a semigroup, but you have restricted multiplication. If you take two elements, it's not guaranteed that you can multiply them together. Or if you are not coming from any of those, then it's like, okay, it's a directed graph, which is closed under composition. So we definitely come from the automata semigroup side. So that's why we write composition a bit differently. We write A, B, C as you would feed it into an automaton instead of the usual category theoretical way. But hopefully it's not too confusing. So sure, I mean, I was like, I need to give a mathematical definition as well. Don't worry, I will give an example as well that will help. But semigroupoid, just like a category, consists of objects, which we might call formal types. Okay, so it's like that's how we introduce types. And of course, this is very abstract. So when I say I'm into types, don't think anything fancy. You can just think about just a peg where you can hang your arrows, because we have arrows, and those also have type depending on their domain and codomain, or source and target. And of course, we are interested in composition. This is the fairly natural. If you have two arrows that they match head to tail, then you can have, and you should have, a third arrow. And I highlighted associativity because that's the property we insist on. So it's like if you multiply or compose three arrows, that's the order of the composition doesn't really matter. So that will be a key thing. But okay, here is the example, because that's the easiest way to think about it. This is a very finite example. So when you do category theory, sometimes you do some very big categories, infinite. But here we just, okay, very small. You have just two objects, sigma and tau, those are the types. And you have these arrows, which later you might think about as functions between them. And in the middle, we have a composition table, or you might call it multiplication table as well. But you see, it is partial. Okay, so that means that, for example, the arrow D cannot be composed with the arrow A. That's why it's empty there. So that's why it's not a semigroup, because in a semigroup, any two elements, they can be composed. And when we think about it, okay, it's like if you order these semigroupoid elements by their type, then you see that you have these blocks. So it's not just any partial multiplication or composition table, but it's sort of like according to their type. You have these blocks in the composition table. Okay, so if you say that, this is still too abstract, well then you can have a transformation representation. I'm talking about exactly the same semigroupoid here, but now inside the object, inside the type, I have these two states, 0 and 1, or 0 prime and 1 prime. And those arrows, they correspond to these functions. Okay, so that's a concrete representation. Okay, so this is the these are the objects I wanted to mention. And now it's like, let's talk about the questions. So it's like, obviously, when you have a mathematical object, you ask, what are those? How many do you have? And it's like, I'm especially interested in the finite semigroupoid. So I'm interested in enumerating them. And then once you have many, you are interested in, it's like, oh, if you have two, how can you decide whether the two semigroupoids are the same? Okay, the directive graph might be drawn in a different way, and the labels might be different, but it's like, are they isomorphic? So that's an important question. And also, what are the different representations and how can we move between them? So I showed you an abstract representation, which is a partial composition table, and I showed you proper sets for each type or each object, and then we have proper functions between them. So it's questions like, if you give me a composition table, what are the possible minimal, in a sense, transformation representations? Okay, so these are the questions we wanted to explore, and so we had this software. We made this software package called Kigen, which means origin in Japanese, and I totally forget why I chose this name, and I didn't even know that Kanren is also a Japanese name. But okay, our stack is we use Clojure before, and that's how we learned about the core.logic implementation of miniKanren, and then it's sort of became clear that, wow, that's a good way to study mathematical objects. So it's like, for better or worse, we actually don't look under the hood. So it's like, I have only a rudimentary understanding what's going on in miniKanren and in core.logic. I just want to use it. Yeah, that's one type of approach. Okay, so first we want to have the enumerating the abstract semigroupoids. So how do we represent them? Well, it's just a composition table. It's just a vector of vectors, and then we have composer, and that's like just to show a very simple goal. And then it's like, well, it succeeds. It's like if the table really has A, B, the product of those two. And I have a little demo. So I think if I do this quickly, yes, then I can show you. So here is one. This is actually a semigroup. So it's the famous flip-flop semigroup, which is just capable of storing one bit of information. And now I can ask the usual question. It's like, well, we can go forward. What is 0 composed with 1? And well, that's 1. That's not too surprising. And but, well, relational programming, you can ask things like find all the pairs composing to 1. And but what we are interested in actually constructing the tables. So we have to do something like that. So what would be all the tables that would have 0 composed with 1 giving 1? And well, of course, this doesn't check any associativity or anything, but that's how we work with Composer. So let me try another quick change. Yes, and so with that, we have to encode the associativity, and we have associativo, and this is for semigroup. So this is fairly straightforward. There is absolutely no problem. We just state that they should compose according to these rules. So we just did it for recreating a previous research. Abstract semigroups have been enumerated before. It's a big, long project up to size 10. So there are a lot of them. But of course, we are interested in semigroupoids, and it gets a bit more complicated. Okay, because we have to deal with the situation where the two elements are not composable, and the logic gets a bit more complicated. But of course, well, yeah, we sorted this one out. This is how it looks like with this keyword, and we just reify that basically they are not composable. And I have to mention the nil fiasco here, because originally we had the idea that, oh, whenever we have a composition table and we cannot compose, the value just should be nil, because that's the most obvious value. What's the result of composition? Nil. And then I try to run the engine on that, and it's like, you know, it was not quite working, to say the least. And then I realized that, oh, what's going on inside? And this is the time where I actually had to look under the hood. It's like, oh, the logic variables, when they don't have any assignment, they are nil. So it's like, yeah, that caused a bit of trouble. But okay, after that, it started working, and then it's like, this fancy n is just another the mathematical notation for the non-composability. But here are these this partial table. These are some examples. This is what we learned from then. And the first one, S1, that looks like a proper good semigroupoid, and it's like, if you look at the diagram, you see that, oh yeah, that's like if A composed with B is C, that's true, which is true in the table. Then this is a valid semigroupoid. But you see it as you don't have many things in there in the table. So it's like, would any table with just a single entry work? And it's not the case, because S2, that's not, it violates associativity. And you see also from the diagram that it's like, yeah, maybe if A would be just a loop as an idempotent, then it would work, but it's not, because A composed with A is not defined, so it has to be a separate arrow. So this started to be interesting. Then it's like, oh, I see, it's almost empty table, and then it's like there is a semigroup behind it. So it's like, I was a bit surprised, although it's like nothing surprising here. You can have a totally empty table, composition table, and that will give you as many different, I think these are just examples of those, many different semigroupoids. These are all type structures that are compatible with this empty composition table. So nothing is composable. So then it's like, well, okay, we thought about that. If you have a a composition table, then it's like, well, you have to check whether the composition is associative, and you also have to check, it seems, that you have a proper type structure. So it's like the arrows, they work out. So we did this type structure inference, and that what it does is like, well, I try to put it into the comments as well, because, well, I don't have the lead bindings before this, so you have to sort of guess it. But it just checks that the compose arrows should have the domain of the first and the codomain of the second, and then it's like, when not composable, they should be distinct. So it's just literally just checking that. And then it's like we concluded that associativity and consistent typing are distinct properties. So you can have a composition table which is like, it's totally consistent with the typing, but this one fails associativity. So it's not even a semigroup. This would be like a semigroup where you have just a single type, or you have just, well, no type at all, if you would say. Or the other one, which is associative, but you don't have the consistent type structure. So yeah, these are distinct properties, but this is how semigroupoids behave. And well, yeah, just maybe just a little demo one more time. Okay, so go there. So yeah, this is the no composition. This is a totally empty composition table. And if I say, it's like, oh, I want to have a type structure inferred for this one, and I want to have just one object. So I'm asking for a semigroup. This is obviously not a semigroup. Yeah, it's empty. And then it's like, if you have two, well, you see, I'm not checking symmetry here. So it's like all the arrows just go uncomposed one direction or the other direction. And just to say that for the flip-flop, we can have the semigroup type structure when you have just a single object. Okay, so back to the slides. So other topics, I mean, we explored a bit more in the paper. I just briefly mentioned them here because we don't want to spend too much time on it. That would be like a longer talk. But then, of course, we were interested in constructing the morphisms. So it is the structure preserving maps from one semigroupoid to the other one. And the key idea was that, okay, we have the composition as a function. So A composed with B is C. So then how to express relations? Well, it's easy. We can just say that A and B are C related. So we have the C relation, all the pairs that compose to C. And the key question is that, oh, what shall we do with the non-composable arrow pairs? And it's like, and you do have a decision there, because if you say that, oh, I want it to be strict, so composable arrows should go to composable arrows and non-composable arrows should go to non-composable arrows. Okay, so that's one way to do it when you consider this and relation as well. So that gives you a stricter morphism. Or you say that, oh, all I care is just to get the composable arrows to composable arrows. And non-composable arrows can go to composable arrows. So that is like, we always want to do this, like mapping everything just to the identity, right? So if we go strict, then we couldn't do that. So yeah, that was the key question there. And then we have this other issue, the arrow type semigroupoid. We called it like this, maybe as like we are waiting for someone coming and telling us like, oh, this has been studied and it has another name. So the idea is that there is always a morphic map. So if you have a semigroupoid structure, you can always have a homomorphism down to the arrow type semigroupoid, where you have a single arrow for a function type. So you only have a single arrow between two objects. And I will show you later, as like we computed this full, it's not full, as infinite table, as like a big table, and try to enumerate the these arrow type semigroupoids. And that's also an interesting story. And then, of course, if you remember, I had the abstract representation of the semigroupoid, and we want to go to a transformation representation. Well, of course, because as we are coming from automata theory, for us, the transformation representation, that's the state transition. So it's like for a semigroupoid, we expect that, or we want to have basically a finite state automaton, but with restricted modes. Okay, that's the idea of the semigroupoid. And you know, we could do this directly. We didn't do that, but it's just we just reused the isomorphism code. Okay, so it's like, and we did this in a semigroup theory. You have the full transformation semigroup containing all possible transformations of a certain degree, a number of states. And then if you want to have like a four-state representation, can you morphically map your semigroup into that? Okay, and if you can, well, there is a four-state representation. If you can't, well, then you could try with 5. And then, so we had, we could do this, but what are the full transformation semigroupoids? Because there is only one full transformation semigroup, but for full transformation semigroupoid, you have many, because you can have an underlying arrow type semigroupoid and then put a number of states there. So it's really a multi-dimensional enumeration. So, well, yeah, I mean, we did a few, but that would require a bit more systematic research on that. So let me just show you. It's back to the arrow type semigroupoid. So this is what we got. So these are the number of dots, the number of objects, and these are the number of arrows. Okay, and obviously you cannot have meaningfully a 3-arrow object with only a single arrow, because then it's like we consider that if you have an object which doesn't have an arrow, not even an identity, then okay, we discard that. And also, after a while, if you have 7 arrows, well, you can't really do that with 2 types, 2 objects. You need to have at least 3. So we did this, I mean, in the paper you see at the bottom as well. These numbers are not on the online encyclopedia of integer sequences. So that means that it's like, oh, maybe no one calculated this before, and maybe that's the reason why there is we couldn't find any name for this arrow type semigroupoids, but we will see. So it's just a bit of reflection on using the core.logic. I would say that the maybe just mine, but the learning curve is a bit steep because documentation is a bit scattered. And yes, I do have the recent schema and all the other books of that type, but it's like when you already want to solve something, it's like, oh, do I have time to sit down and read those books? Because obviously the answer is there. So that's a bit difficult, and I'm happy to see that there is work going in the direction of working with sets, but that would be also quite useful. But what we would like to have is that working with hash maps, because that's what at least I do in Clojure all the time. So when we go relational, we need to convert the algorithms to the list-based operations. And also, it's like when we did the enumeration for the semigroups, you want to exclude all the 3 nilpotent ones. Most of them are non-interesting. You have 3 elements, you multiply them, you get a 0. So it's like, would be interesting how to express this thing, excluding the 3 nilpotency. But okay, I think my time is up. So let me just end here. Thank you.
I presume we have 1 minute for questions, so perhaps 1 question can be asked. No? Yeah.
I guess just out of curiosity, you showed this big table of numbers you generated for how many of these semigroupoids there are. How much time did that take?
Well, yeah, where it ends, I started running the search like 2 weeks ago, and hoping that it's like, yeah, 2 weeks time. So there are several tricks. We can be clever. We can do that, but it's like 2 weeks time. There was nothing. And I don't know. The isomorphism checking takes a lot of time because you want to check that up to isomorphism how many you have, and then it's like if you have a big isomorphism class already, you have to check all of them, and then it's like all of them would do the full run. So yeah, this graph isomorphism, it's like it's difficult to calculate.
Yeah, thank you.
Thank you. Let's thank the presenters once more. And finally, the next talk is on visualizing miniKanren search by Jason Heeman and Bryson Hingston, who will present the talk right now.
Yes, so hello, my name is Bryson Finkston. This is work done with my advisor, Jason Heeman, so I'll be talking about visualizing miniKanren search with a fine-grained small step semantics. So we'll start out with a little introduction, a sort of thought experiment, then we'll get into the semantics, then we'll do a demo of the visualizer, and finally we'll conclude. So small step semantics are a great thing. It lets you prove things like program equivalence, type soundness, safety. It helps with reasoning about your programs, which in a language like miniKanren, which is very declarative, is nice because your search strategy is coupled with your implementation. So if you were to want to understand that, you'd have to go read your implementation. So something like a semantics for that formalizes it is great. And implementation, the reduction steps themselves correspond with what you would see in your interpreter. And so it's been done for a variety of languages, including JavaScript, which is everyone here's favorite language. And so when you're building up a semantics for your language, it's really important to understand what your values are, because the values are the things you're reducing towards, and they're the things that you stop reducing at. So in Racket, you might put this expression into your REPL and get out that list. In Python, you might do something very similar. And in miniKanren, you could do a run query with Appendo, and you'll get something that looks very similar to what you got in the racket. So when you're thinking about your values here, you might be tempted to say, well, whenever I put something in my REPL, the values are the sort of things I get out. And miniKanren being an embedded language, you might say, well, my values are just the values of the host language. But if you're actually implement miniKanren yourself, a more nuanced take would be that the values are substitutions. So we're mapping logic variables to the host language values and other logic variables. And the thing you see in your REPL is really just the reified version of that substitution. But I'm going to take that one step further and say the values are a tree containing success nodes and their substitutions. So the intuition here now is that we have expressions, which are trees, and our values are also trees. So at a high level, our semantics are just tree-to-tree transformations. So we have two contributions. The first is that small step operational semantics, which is deterministic transformations of the search tree. They're operating at the level of individual goal evaluations. So we're operating below the level of the interleave, and we mechanize these semantics in PLT redex. And with that, we'll also validate some properties of the semantics. Secondly, we have a tree-based visual stepper, which is a web app, so there's no need for local installation, and we use those semantics at the core. So getting into the semantics, we'll assume some term language here. What's important here is our relation names are with R, and our variables are with X, so those will come up later. And we have the usual state consisting of a substitution mapping logic variables to terms and a logic variable counter. So we mentioned trees are our main thing, our expressions and our values. And so our program consists of some relational environment and some search tree. And our search tree could be empty, which represents failure. It could be a goal state. It could be a disjunction of two search trees or a conjunction with a search tree and a goal. Here, we'll look at goal states. So in order to understand our goal states, we have to understand what our goals are. And so for those, we have the T symbol, which represents success. We can unify two terms. We have disjunction, conjunction, and fresh. And so the semantics themselves are actually small enough where we can go over them in their entirety, albeit kind of quickly. So starting with our goal, the unifications. So for each example, I'll show you a pictorial representation, which is something like a minimal or most general example. So on the left, we have the rule for unify succeed. So if those two terms do unify, we update our substitution and we replace it with the success node. If unify fails, then we will replace it with that empty node. And for disjunction, we will simply distribute the state over the two goals. For conjunction, we'll give that state to the first goal and leave the second goal as it is. For fresh, we do the standard, we increment our logic variable counter, and we substitute the variables the user wrote with the logic variables. So visually here, you don't get to see much, but we evaluate that goal below the fresh with the updated state. Right, so coming back to our trees, so there's no strong way to motivate this, I think, except with an example. But right now, our disjunction is just a single plus. And so if we were to want to interleave those trees, we'd have to actually swap the order of those trees. So visually, what that would look like, and the actual tree itself here is important, but we have some tree that we're going to interleave, and we'd have to swap the two trees. And so visually, that can be pretty disorienting. You can imagine having a much larger tree or having nested disjunctions that you have to interleave. And so rather than doing that, we'll start with the tree, and the interleaving will simply change the route where evaluation is continuing. And so we call this the railway model because it's like switching the railway tracks. So rather than moving the actual tracks themselves, you're just switching which way they go. And so to do that, we just have two types of disjunctions, one facing right and one facing left. And we'll reserve that plus operator for our answer stream. So our answer stream consists of some answer appended to another search tree. And for interleaving, we'll introduce two control operators, delay and go. They're pretty obvious what they're doing. Go tells you evaluation can proceed down this tree, and delay just represents that tree is suspended. And one goal that I failed to mention, or I guess I delayed mentioning, is our relation calls. And they're special in that that is our delay points. And so now that we have all of our trees, we could start talking about our evaluation context. So the first one, EP, just steps down into the search tree component of our program. Then EA for our answer stream, we step past all the answers we've accumulated. ES, the third one, is for stepping down into the subtrees. So we follow our disjunctions. So for the left-facing disjunction, we go down the left tree. Similar for the right. And for the conjunction, we just go down the search tree component. And the one we'll be using the most is that last one, which is just a composition of the three. Right, so getting into interleaving, I mentioned that relation calls are our delay points. So whenever we encounter a relation call, we'll double wrap it with a delay and go. And the reason we double wrap it is because this will give us effectively a lazy expansion of a relation call. Because we know we're delaying it, there's no need to expand it immediately, especially in the visualization where that could clutter up your screen. And so this is when we would actually expand it. So after we interleave and come back, and we see a relation call with go on it, we'll grab our relation definition out of the environment and substitute the terms into that goal. Yes, and so this is the interleaving. So if we have, and also for the railway model, we're going to have some combinatorial effects. So here we have a disjunction, so we're going to have two. We have to handle the case where it's facing left and the one where it's facing right. I will only show the ones facing left, but the ones facing right are something like the symmetric version of what I'm showing you. So we have a disjunction facing out a delay, so we'll propagate that delay up above the disjunction, but we'll also flip the way the arrow's pointing. So you'll see here, it was starting left, we delayed, interleaved it, and now it's facing right. For conjunction, we simply just lift up that delay above the conjunction as we can't interleave conjunctions. And the way we get rid of these delays is, if you'll notice, we're matching on a different evaluation context. So we're only going into the program and through the answer stream. So we're effectively right below our answer stream. And so that means the delay has reached the top of the search tree, really. And so we can release it at that point. Yes, so that was interleaving. Now we could deal with some tree transformations. So the way we propagate our successes up, you'll see here we have nested disjunctions. And so the idea here is you have some nested disjunction facing at a success node. And so what we'll do is we'll lift that success node up and pull the other trees down. And so if we have a disjunction with a success node within a conjunction, it will either be a conjunction between that success node and the goal that was waiting, or the other tree and the goal that was waiting. And this is how we actually promote a success node to an answer. So once a success node reaches the top of the tree, it will say is now an answer and there's no more work to be done on it. And for conjunctions, if we have a success node, we need to take the state out of that success and evaluate the goal that was waiting in that state. And lastly, pruning, so we don't model failure within our trees. So as soon as we fail, we want to prune that subtree. So if we're pointing at a failure node in a disjunction, then we'll just get rid of it and evaluate the other tree. And at conjunction, we would say the whole conjunction fails. So that's the semantics part. Next is the visualizer. So there's some existing logic programming tools, like the bird box was very popular with Prolog. It's also called the 4-port model because you have those 4 ports, call, exit, redo, fail. And there's also and/or trees were pretty popular. The and/or trees are much more similar to what we'll be doing. We'll be showing an actual tree representation of the program. There has been some miniKanren tooling as well. So this work by Bird et al. A different bird, I'm assuming there's no relation. But what they did was they defunctionalized the higher order implementation of miniKanren. And once you have that defunctionalization, you have a first order representation, which is independent of any given search strategy. So you could do some cool things like have a user guided search or neural guided search. But theirs is a textual stepper, and it's not as granular as ours. So, demo time. Yes. So this is the UI for our website. So on the left-hand side, we have where you input your program, and the concrete syntax we accept is just the core miniKanren Lisp scheme racket style. So we don't support things like disequality or the type-like predicates. On the right here, we have the tree canvas, which we'll see later. We have a sidebar to inspect the state information. We have dark mode if that's your thing, but I'm going to make you look at the light mode. At the top here, we have what step you're on and the name of that step. And so that's the gist of the UI. We have these 4 buttons: start, reset, back, step. So I'll go ahead and load a program from our list. And when we hit start, it will pull up the tree. And so one nice thing you can do is you can click on the node in the tree, and it will show you where it corresponds to in the source code. So this first fresh corresponds to the entire run query. this fresh would correspond to the first fresh in the run query. And we can click on the source code as well, and you'll see that it highlights the little unification here at the bottom. And a nice thing you could do with that is you can click on a node, and it sort of subscribes you to a state. And what I mean by that is as we step, it will show you in the source code where that state got moved to. So we are now on this fresh, and if we keep stepping, we have a long list of conjunctions, and so we're going to distribute the state down those conjunctions until we get to this first unification. We'll evaluate that, it will succeed. And another nice thing we have is that you can hover over a node and you can see its reified form. So being able to see the reification before it actually becomes an answer is kind of nice, because as you can see here, we know what the structure of the answer has to be without knowing its components. And that's something you see often is you conform the structure, or you constrain the structure to be something before you constrain the components of that structure. So here we have a list of 5 elements. And so if we were to click on this and open the sidebar, we could see that was added to our substitution. The first logic variable was a list with 6 elements with the empty list. And so as we step through, we can see, so let me step back actually. We can see that A has been added to the list, now B has been added to the list. Yeah. So if we step all the way up, we could see our answer is the list A, B, C, D, E, F is what we expected. So that's like tracing and looking at the state information. This program was from the last workshop, and it essentially just enumerates some little Indian byte vectors that are divisible by 3. So this is a fairly large program. So this will show you interleaving and how we lazily expand our relation calls. So if we step through, we'll get our base case, which is the empty list, and then we will expand that same count relation. And it's a pretty big tree. So we'll step through, we get another answer, which we can inspect as the list 1-1. And we can keep stepping until we get down to this relation call. So if you follow the line down the tree, that will show you where the evaluation context is at. So we're looking at this relation call that we haven't seen before. So what we'll do is we'll add a delay and we'll mark it as go, which is green. And then we'll move that delay up, we'll interleave, so now the arrow is facing right, and then we can proceed evaluation down the right-hand side. And so you'll notice we haven't actually expanded the same count though, and we'll only get to it once either the other branch fails or succeeds, or if we encounter another delay. So here, we encounter mod plus 1-0, we add a delay, we push that up, and it hits the answer stream, and so we release that delay, and now we're facing the same count though, and we can continue evaluation with that. The last example is just the classic appendo, but with this one I want to show you a new concept, which is the trail. So if our first one's going to fail, but then we'll go down into it and we'll hit this unification. And so we'll see we unified the list miniKanren with cons logic variable 1, logic variable 2. So we'd expect 1 to be mapped to miniKanren and 2 to the empty list, which is what we see. But if you're keen, you saw this other part of the thing, which is the trail. And so the difference between a trail and a substitution is the trail contains the actual terms that were unified. So with the substitution, you're seeing the mappings that were required to unify them, but you don't see the actual terms that unified. And so that's nice because deep within evaluation, you might want to know that 1 and 2 came from unifying a list, versus here, it very well could have been 1 and 2 were unified separately. So that's good for the demo. Yes. Right, so this is how we would update the unify succeed rule. We basically add a new component to our state, which is the trail, the little T symbol, and then we update that when unify succeeds, we walk the terms and add them to the trail. So as I mentioned, we mechanize this in Redux, and so with that we can validate some properties by synthesizing programs and running tests against them. So one is that every well-formed program is deterministic, so we'll never step to more than one tree, and the other one is syntactic preservation, so you'll never step from a well-formed program to a non-well-formed program. And the nice thing about reduction semantics is that they're really modular, and so we also implemented depth-first search semantics, which you can really easily derive from the ones we did. In fact, if all you had was an eraser or a backspace key, you could take the semantics we had and create a depth first search one. And what's nice about this is it runs on the same program base. So you could run the same program with a depth first search semantics or an interleaving semantics. So you could show how a depth first search would infinitely starve a branch, but our interleaving search wouldn't. And there's also another paper describing an operational semantics for miniKanren from Rosenblatt et al., and we implemented theirs. They just have more delay points, but we extended it with an explicit answer stream, the trail, and the railway model that you saw. So future work would be making it more of a debugger and less of a visual stepper. So you might want features like fast forwarding, you might want to step over a relation call, maybe some profiling features, breakpoints, etc. For scalability in UI, maybe stepping away from Redux and rolling our own implementation with nicer data structures can make it faster. You might, in the UI, want to collapse very large trees or the suspended trees. A user study, I think this would primarily be focused at students, seeing if students learn logic programming better with a tool like this. Some more semantics, so maybe something like a continuation-based semantics or iterative deepening depth first search would be nice, and comparative semantics. So compare what we have to an existing implementation, possibly prove that they're equivalent. So to conclude, we've presented semantics, a small step operational semantics from miniKanren that makes the interleaving strategy explicit, and we use those semantics to build up a visualizer where the user can see the tree transformation step by step. We hope this will support clearer reasoning and understanding of logic programming and potentially some experimentation with some more semantics, and also for teaching students, I think it'd be a great tool. So a QR code for the tool is on the top and the source code is on the bottom. Thank you.
Okay. The mic needs some time to warm up when I switch it on. We have plenty of time for questions. Please ask questions. Yeah.
Hello, yeah, great talk and very cool stuff. One thing I was wondering, so right now, so I guess a sort of known issue with miniKanren is that when exploring disjunctions with the interleaved approach, some branches get much more time than others just because there's a sort of hierarchical approach. But I was wondering if you think the sort of railroad method could diagram two railroads that have more than two tracks, but then still sort of do the interleave stuff, and then so that you can have disjunctions of multiple things that is potentially a more fair search. Any thoughts about that?
Yeah, so right now our disjunctions are just binary. So there's only like one meaning there's left, or two meanings there's left and right. So are you suggesting like arbitrary number of? Yeah, that could be interesting. I don't know what to say much about it, but yeah.
Thank you for your talk. I have a question. Why do you need different leftist and rightist disjunctions in your model, in your semantics? I think it only requires you to doubling some rules and don't give you impact.
Yeah, so it was actually something we added later. So we had a semantics that was just the one disjunction. But the reason I even showed you it was just to connect it to the visualizer. So the semantics and the visualizer themselves are very coupled. So I think, yeah. So there's other ways you could do it. So maybe you want to like keep a track of how many times this branch has been interleaved, and then based on if it's even or odd, you would know which way to go down. But yeah, you could derive a very or directly equivalent semantics by just removing that, and then during your interleaves actually swapping the trees. But it's primarily just for the visualizer.
Yeah, thank you. It's a very good work. Quick question about the back button. So you say you can step like set down, right?
Yes.
So to go back, are you using your small steps operational semantics here, or you just save the previous history in your front end so you can go back?
No, so there's no way you can know going backwards. So yeah, it's all just cached.
Yeah, so this is what I mean, like you save your history in your front end, so when you hit the back button, you basically go back to your history.
Yeah,
Yeah, okay,
it's
thank
all
you.
cached, yeah. And if you step backwards and go forwards, that's also still cached.
Great talk and very interesting tool. I was wondering what the connection is between the front end and the back end. So, for instance, is the semantics that you showed, you said you mechanized in PLT-REDX. Is it that mechanization which is turned into the front end such that I could change the PLT-REDX code and have that reified on the front end? Or are they different, just kind of implementations of the same semantics, and I'd need to change the actual, I assume, JavaScript implementation in the front end if I wanted to, for instance, add constraints or lazy goals or something of the kind?
Yeah, so the front end actually does not a whole lot. Like, it really just renders the tree for you. That's about it. So if you wanted to like add more operations or node types, that would be the semantics and the visualization are coupled. But yeah, I mean, essentially what you do is you have your program and you can serialize it as JSON and pass that over to the front end, and then the front end knows how to draw the JSON style tree. Did I answer that? Right.
Yeah, so if I understand correctly, the actual implementation of the stepper doesn't happen in the browser. It communicates with a back-end implementation, which is actually running the PLT-REDX implementation?
Yeah, so basically Redux provides a way where you can just say, give me the next step. And so you get the next step, you send that back, and then whenever the web browser asks for the next step, all it does is step the program one time, updates the state, and then sends it back over as JSON.
Great, thanks.
Just to try to add one more thing. I remember Wilbert make something sort of like relational things. So I'm still thinking about your back features. Like maybe if you use that, like you can implement the things like going back.
Yeah, maybe. There's definitely, how we're doing it now is definitely not optimized. There's certainly a better data structure because you're essentially rewriting just subtrees, but right now we're copying the whole tree.
Yeah.
So maybe storing like the deltas, like, okay, there's only this subtree that changed, and you can use that to reconstruct the previous tree would be more optimal. But you mentioned doing that relationally.
Yeah, like you make it relationally. Like you go back, you still can go back.
Yeah, I just don't know if you can reconstruct it perfectly going backwards. I think there's just not enough knowledge there.
Okay, more questions? Well, then I have the one. I played a little bit with your tool, and I got an impression that in order to understand what's happening, you need to familiarize yourself with the semantics. So you need to study the semantics first.
Mm-hmm.
Can you elaborate a little more about if this tool can be used to study the semantics without knowing the rules of reduction?
Yeah, so you're saying you need to understand the semantics to understand what's happening to the tree?
Yes, yes.
I think the fact that it shows you where the evaluation's happening, and also it shows you the name of the step, I think you can learn the semantics through the tool. So if you look at a tree, it's a fun exercise to say what's going to happen next. And I think doing that repeatedly, you build up an intuition for what's happening with the semantics.
Okay, perhaps we need to test it on someone who doesn't know the semantics of miniKanren.
Yeah.
Yeah. Do we have any questions? We don't have more time for them. Thank you very much. And this concludes the third session. Thank you.
All right, well, at this time, as chief head panelist and also furniture mover, I'm gonna, oh, I forgot about that. 3, possibly 4, because I could be a person. And what I was thinking, as I was hoping I could get Michael and Dimitri and Santiago to come on down, and I've got a mic. You all have to share 1 or 2 of them. Oh, I tell you what, I'll hand these to you.
Testing.
All the mics.
Well, I can do this one.
Yeah.
Then this one can go back to the audience. Oh, right. Can you like tap it, please? To this side over there, face the two of them.
Can I hit the power button? And then
No, we're fine. We're fine.
Turn it off from our side.
Okay, because it looked like the sun.
You have one mic, okay.
Mic check.
Pretty much for everyone.
No, your guys' are not working.
Yeah, we're not.
Oh.
Oh, there we are. Mic.
Speak? Oh?
Are we back on? It worked for a second.
Oh, yours,
Is that good?
I think yours might.
Yeah, I'm good.
Really bad. I'm really, really sorry about this. Okay. How about we clip them to the collar?
Yeah, that might be better.
No, that works. Check. That works?
Yeah.
How about you?
And for me? No, not yet.
Not yet?
1 of 2.
Nice.
I can get very close to you.
Michael, how are you?
I'm fine.
I mean, and your mic?
Does this work? Yes. Maybe
Maybe
not so
like
close. Here?
Here. Yeah.
Okay.
Dimitri, how?
No, I don't think so.
Hold on.
It doesn't work.
Put it down and try speaking.
Yeah. Okay. Okay.
Alrighty.
1, 2, 3.
Cool. Well,
If it doesn't.
Yeah.
this is the last slot of the last session of the miniKanren workshop today, and I guess first of all, I'm going to ask this question to the panel. What does it say that I need to apologize to the audience that there's another miniKanren talk going on at this same time at another workshop? Like, what does that say about success? You can also comment on the organizing on my part, but what do we think? Is this a sign of that miniKanren has reached kind of permanent ICFP level status?
Hell yeah. 11 papers this time? That is very impressive.
As far as I remember, they used to be a workshop with 12 papers.
12 papers,
Yes,
all right.
So,
well, next year.
Yeah, this is the second largest.
What's the talk we're missing?
Another type Karen talk, actually.
Ah, okay.
So, luckily also being recorded. Well, I guess maybe to dig in a little bit deeper, and I'm so glad to be here because I get to pepper some experts with questions of things, and I get to say it's on behalf of the audience.
Experts is a stretch.
So what is miniKanren? What is relational programming, and how do we treat these? This is what we're doing as an entity separate, or its relationship to traditional logic programming, CLP, database stuff. We have variants where we've replaced the term language, variants where we've replaced the search with neural search, variants where we've replaced the host language, concrete and abstract syntax, and different representations, visual, textual. When does it stop becoming a miniKanren? Is this going to eat the earth? Do we have a ship of Theseus problem? What precisely are the boundaries of what we're doing here?
I presume we're all doing different things because we like different things, fortunately. This is a little different for every of us. So we see things different.
And what's the thing that we've got that's in common? Like, what ties us all together other than being here at 4:30 on the second to last day of ICFP? What makes it all one enterprise? I guess another way to ask this is, there's been a lot of explorations in a lot of directions. Are we converging on like one common understanding of what it is that we've been groping for? Do we feel like this is fragmenting into many different directions? What does this variety say about the future direction or directions of miniKanren as a community growth?
I have a hypothesis. This is just another level of declarativity. So when we do functional programming, for example, or stateless programming, we strive to write the program more declaratively, not in the terms of computational steps, but in terms of semantics. Right? When we write in Haskell factorial like prod bracket 1 dot dot, and this is a specification, right? So in the compiler, the system does its job in order to provide a good implementation. And this is just yet another step in order to achieve better, more declarativity. This is my vision. I might be mistaken.
I mean, I think that's certainly what some of us are trying to do. But I'm trying to go the other way. I'm not trying to add more declarativity. I'm trying to restrict declarative things until I know that they can actually solve stuff, right? I'm coming at this from the databases end and the finite end of things. And so I'm interested in what chunk of declarative programming I can have and still be guaranteed that it solves it in an efficient way. So that's actually cutting down what you do in the declarative bit, rather than trying to envelop the function.
Yeah, I presume that this works as both ways, because one people just rise at the level of abstraction, and the others try to make efficient implementation of what those people invented, right? So I don't see any contradiction. So, because it just makes no sense if you can't run your program, right? So it has to be some way to implement efficiently all these levels of abstraction, all these semantical features, these optimizations, etc., etc., etc. And it took a lot of time for functional programming to become applicable, because
I don't know, if I had to pick something that's unifying, it would be, well, relations, in some sense, right? And if I had to say what a relation is, well, I had a talk on this at Hope, kind of, or a talk where I said what I think relations are at the Hope workshop, which is they're functions with support, right? A relation, mathematically, forget about programming, the function into booleans tells you whether the thing's in the relation or not in the relation. But in functional programming, functions are input-output black boxes. You need to give the inputs and you get the output. Relational programming is where we don't want that. We want to be able to run it the other way and get the inputs for which the output is interesting, right? So for booleans, that's the ones where the output is true, where it's in the relation. So why, you asked, like, are we fragmenting or are we unifying? I don't know, I think relational programming has been fragmented for a long while now because we've got so many different ways to represent relations. You know, that I talked about databases and logic, right? Do you do it bottom up? Are you representing relations by literally tabling them? Or are you, representing them by streams of things that represent a solver state that say, here's my logic variables, here's my substitution. And there's other ways too, right? The constraint people have their own fancy solver states. So I think relational programming has and will continue to be fragmented, but we're unified by being interested in relations. Something that tells you what the interesting inputs are, not just takes inputs to outputs. I don't know, does that feel like it makes sense?
Yeah, it's exactly what I meant, because this is
Mic
just...
closer? Okay, sorry.
Because this is just the raise of the level of declarativity. You just generalize the notion of functions. The next step is a relation without any limitations. So it's exactly the same.
Well, I was going to ask, is there anything that's currently kind of holding us back? And that might, do you think of that as one? I was considering on the axis of things either theoretical, practical, cultural, either within or within the surroundings. Is there anything we can do to put off the brakes and turn on the gas and make this go faster?
I can talk a little bit about this. I'm a little bit of an outsider trying to come into the community and benefit from all the great things that have been invented. We were really attracted by how easy it is to customize miniKanren and how much has been done around it. So it's really easy to grab any paper and be like, now I have a new feature and add that. So that is the great thing. On the same side, what we just said, which is this fragmentation, makes it that it is really hard to know which ones play nicely, and there's very hard to find really clear comparisons and benchmarking and knowing those are the things that are gonna work well together. So to me, that is the limitation. And it's like, it would be great to have a framework that unifies everything. I know I'm asking a lot, but that is kind of the direction that you would love to see.
Can you give me some low-hanging fruit that we could start on? A couple people have said, Jason, you really need to do something about that miniKanren website. I see things like CBC4 that have like you step in and try it on the web, and they don't list every implementation of microKanren that I've ever found.
Well, let's start with like, I don't know, can you imagine a graphical interpretation that you could step through the relations? That would be a great idea.
That would be a cool idea, yeah.
I mean,
go ahead.
I didn't know that the canonical modern miniKanren implementation was faster than miniKanren until someone said it in session.
All right, that's our GHC, I guess.
Centering some knowledge about where you should start would be great.
Yeah, and I guess I think I want to separate probably the general implementation strategy from necessarily one in Racket, because I think the Dimitri and his OKanren folk are also doing some very cool stuff. They've certainly picked up some of those implementations and run with them, and they have a few of their own. That was another thing I think somebody had mentioned. I'm on this web page, I heard about this miniKanren thing, I want to try it, and then click on it, and what do I download and how do I use it? And I don't, is in 2025 that not a reasonable question to have an answer to? Do any of you guys do web design? Do any of you guys do web design?
Yes.
My day job.
All right, well.
Congratulations, yes.
Oh, yeah, boy, I can tell you're new to this area. All right, that's the level of like kind of practical friction removing stuff that I can think of. So graphical tooling, that's not bad. What else, that doesn't really require research can we do to just make things easier? Or broaden the community?
Yeah, it seems to me that it's too early for us to have a unified framework, because we need, there are too many options we need to investigate further in order to understand how all these features can coexist. And again, taking as a sample functional programming, it took almost 50 years to elaborate common patterns, common tools. Because in 70s or 80s, if you look at the functional program conference, we were filled with marginals. Nobody knew what functional programming was for, and then nobody believed. Even I remember at the time when nobody believed in functional programming. And now functional programming took over the world because every mainstream language has first-class functions. So I presume we need to enjoy our opportunity to not be in the mainstream, to not to take over the world, because we can do many interesting stuff independently.
Let's enjoy our adolescence to grow and explore.
Yes. So
well, Dmitry, I think you're we're all here because of Ilya, but I think you're here because of Ilya twice, right? I was going to ask you. You were talked about people believing and not believing. I think you were one that somehow got seduced into this by Will and Ilya. What grabbed you about this? What made you? Because that's a decent shift in a research perspective to say I'm going to become a miniKanren guy now. What made you bite so hard?
Well, it's okay. Well, actually, I started as a software engineer, and I worked as a software engineer for almost 20 years. I used to work for JetBrains, for example, before I got laboratory at JetBrains Research, and I tried to read and learn and study various things, and I stumbled upon Prolog, and I read some samples from Prolog, not being able to reproduce them because I don't have Prolog at my hands at the time. And for me, it looked like pure magic, and I was completely sure by the time that it's so complicated math and in computer science, which I will never be able of understanding in depth. So I given up on Prolog. And then many years after that, when we have an opportunity to invite Wilbur to conduct our summer school on relational programming, there were multiple choices for me to choose from instructors, and I choose Will because the area he worked in was completely foreign to me. I knew nothing about relational programming, so I invited Will to familiarize ourselves with this area. And Will later told me that when I invited him, he thought, oh, okay, they know what relational programming is, they are interested. It was quite the opposite. I invited him because I didn't know anything about relational programming. And when he showed us what relational programming is, I immediately remember the Prolog and those troubles I had understanding the semantics. And this time, this approach just seems to me so elegant, so simple, and so powerful that I just canceled all my other research and switched to relational programming. That's the short story.
Okay.
Yeah.
Santiago, did you have any of those same feelings in your heart?
Oh yeah. Our story's pretty good. I mean, I told the abstract part of it, which is we wanted to do things quick, and we thought that this was the best way to do it. But the reality is we just thought it was very cool, and we wanted an excuse to do it. I must confess that the first step to it was David suggested the idea. I said, you're insane, that will never work. But I do respect David, so I went for a week and was like, I'm going to implement it and show you that this will never work. And then I got super excited about it and came back next week and I was like, can you believe that this really works? And it was like a tiny implementation. We had a tiny compiler and it worked both ways, lambda calculus to some imperative language. And I was like, I don't even know why it works. I implemented it and it seems like magic. So that excitement kind of carried us to the development.
So it seems like pretty uncontroversial to say it's important for a language and a community to be driven by practical real-world concerns and practical real-world users. And I don't know if is this being recorded? I don't know if we've ever had users on the scale of people who hand out T-shirts at conferences. So, like, what other uses are you waiting for? What features do you wish? If you had a team of people in a room and you could try and convince them to work on something to make miniKanren more useful for you and like selling widgets, what would they be?
In reality, it is efficiency. That's really what's going to get you there. I can work on the ergonomics and nice features and make my engineers and convince my engineers to work on them. But at the end, if we can't scale, there's just no future. In practical ideas, I have many ideas of things that I would like to apply miniKanren to, and our ideas of compilation, transpilation, and so on. And I'm way less worried about features, which I believe that we'll figure it out, than to make things scalable. That's the reality.
Michael, I feel like some of that is your concern too, in getting it. Most of my programs don't scale to the millions of examples that quickly like yours do.
Yeah, I guess I'm coming at it from the other end, which is people definitely use databases. They definitely hand out T-shirts. So can we take databases, take the tech that makes them work, and just push it to be a little more easy to use in general programming, make it a little more expressive, combine it with stuff that people already like functional programming. So it's sort of the other end, but this isn't really miniKanren. There's definitely points of intersection, but yeah,
and can you remind me where? Can you remind me where I think data fun fits in this? Is there a? Because you've done some Datalog plus work. Can I squint at that and look at a miniKanren little brother? Is that?
I mean, I don't know. I guess this depends upon like where does stuff stop being Kanren-ish, because it's all definitely bottom up. All of the stuff I've worked on is pretty much bottom up, and so if you think bottom up can count as miniKanren, then yes.
Does it matter?
Does it matter? I mean, it definitely changes the kinds of programs you can write. You can't write an existential without something that's going to ground that existential in my world, right? Which stops you from generating quines, for sure. Yeah, some sort of story about how bottom up and top down can coexist could be cool. Obviously, people have tried that before.
So we've had tabling and things like that. And I know Will's dissertation spends several chapters on tabling in miniKanren, and I don't know who's picked up that torch since then. Well, I don't know. Let me bring this out to the larger audience. When does it stop being a Kanren? Somebody, anybody I've got a piece of software in front of me. What poke or prod would I tell to tell me if it's a Kanren?
Does it quine?
Does it quine? That ain't bad.
Yeah.
Why is that example so darn compelling?
Because it's cool. Like, obviously. I mean, maybe it's the magic factor too. I mean, like, I got interested in relational programming when I started realizing it wasn't magic. I don't know if that's some people get interested because it feels like magic. I got interested when I started being able to feel like I understood it. So I don't know where to go with that thought, but. We need to get the audience to speak. The audience hasn't spoken yet.
All right, I'm gonna start calling on people.
So, coming from Prolog, I want to hear a lot more about how you think miniKanren currently compares. If I look at Prolog, how I learned it at uni versus how I sort of refound it years later on the internet by Marcus Triska explaining me how to actually write Prolog, the main difference was actually use logical purity and never use illogical or extralogical predicates. And then there was the addition of CLP FD which is essentially to me sort of the more data structures or standard library approach to make it more feasible to write stuff that actually works. So when you look at miniKanren, I'm hearing a lot of those same themes. I was just trying to look up the will on the difference between Prolog and miniKanren, but I didn't speed read it right now. But maybe you could say a little bit about the difference currently as it stands, more towards modern Prolog and then miniKanren.
Yeah, Dimitri is my former Prolog devotee. You want to take a stab at it?
Yep. Both languages, both approaches seem quite close to one to another, but there are essential differences. And differences come not only from design choices, but from the very time in which these approaches were developed. Because Prolog was developed in the 70s as a mean to implement one of the first theorem provers. And it's developed for completely different computational environment, slow machines with a small amount of memory. So, the difference in search is not essential. It can be implemented both ways. But the key point in Prolog implementation is that there is an abstract machine or an abstract machine which made use of the properties of the hardware it was run on. And that was the key point of Prolog success. And these properties are non-compatible with interleaving and et cetera, et cetera, et cetera. So the depth-first search was the only possible way to implement the search efficiently at that time. So this is what I know about Prolog. And the second feature of Prolog is it builds a closed ecosystem. If you start writing in Prolog, you need to write everything in Prolog. Because that was the approach to language development at the time. They were believing that there are generations of languages, and eventually there will be the language, the only programming language, and Prolog was one of those candidates. And this is completely incompatible with current zoo of languages with interoperability. So problem with Prolog is that it just was built in completely different environment, and the design choices are not compatible with current design choices, with current trends. That's my opinion. And in order to do logical search, do search, solving puzzles in Prolog, you need just to give up on other languages and implement everything in Prolog. And in contrast, you have a tiny DSL which you can implement easily in your favorite language. And you can implement only the search, and all other environment around the search, like input-output files, user interface, you can write in your favorite frameworks.
Well, you say that, Dimitri, but how many lines of code now is OKanren?
Sorry?
How many lines of code is the implementation of OKanren? Because
I don't know it. Few thousands of lines.
Is there something like do we lose is that tiny DSL story still true to get the kind of efficiency that Santiago wants?
Okay. You still can have almost seamless integration of OKanren code with OCaml. So, and the code base of OKanren is so large because we implemented a lot of optimizations. And it's still not as large as other libraries in the OCaml world. So
if I'm reading that right, it's the EDSL part more than the small, tiny size.
Yeah.
We live in a multilingual world. miniKanren knows how to play well with
Yeah,
others.
but when you do not have a ready implementation, and you have, for example, almost each year I have a student who implements miniKanren in a new language. In Kotlin, in Tanzen, now we have some work, etc., etc. It's tractable for bachelor thesis students. So it's of course, in order to get the most of efficiency, you need to re-implement, reify, and reiterate this implementation. But the first results can be achieved much more quickly than if you need to implement Prolog.
Yeah, I echo that. That was exactly the reason we picked miniKanren, because we wanted to play with it, we want to customize it, and implement it on Prolog seemed like an unachievable goal in the time we had.
I wanted to add a couple of things. Thank you for the discussion. I didn't mean to make this all about Prolog, by the way, but the last I've seen from the Prolog community is that they realize the main thing they want to work on is interoperability with Python. So I think miniKanren is way ahead here, right, in terms of playing nice with languages. And then I think miniKanren, more examples of how to write programs and a more of a standard library approach of this is the tools you can use would be a great focus.
I think Marcus's textbook, I think that is a great book on just whatever your favorite language is, doing declarative programming in a logic relational style. And I wish we had something like that that was miniKanren native or even translated. And yeah, a nice corpus of programs. It would be good to have, I don't know, a nice text of curated best-in-breed examples. I've seen people in the Prolog education community recently suggesting that we need to have, they wanted to have somebody who wants to pick it up and learn how to write these things nicely. I don't know, anybody who's new, where have you been going to learn how to do this nicely? Where's your corpus of examples you've been learning from? Nobody got one? Oh, Mike.
I guess I started with the Reason Schemer 2. So it sounds like if you want a new textbook with lots of examples, and maybe there's a Reason Schemer 3
Oh boy, this
that
is
needs to be made.
Oh, well done, sir. Oh no. Sure is fun whitewashing those fences.
I know when I was getting back into learning how to use miniKanren, I went on the website and I found some sort of documentation. That was originally where I went through when I was trying to figure out if it would work for the problem I was trying to solve.
Is there a Stack Exchange for miniKanren?
That's a great question.
I know there are still, well, back before the Gen AI thing, there were people asking occasional questions. They get good answers, but I think more traffic and questions and more traffic and answers would be nice. All right, yeah, this is another one for the whole team to play along. If you had unlimited time or a grant just to explore some particular one question about relational programming, what would it be? Give me the first 2 or 3 sentences of your abstract for that.
Well, actually, I apologize in advance for this question, but how can we coexist with modern AI?
That's good.
Because I think we can coexist. Actually, there is sort of nonsense that we can have in software engineering, information technology, a separate area called AI, because all information technology is about AI, right? So, and not much people know that actually the original meaning for AI was what we are doing here. So I don't mind taking the term, but we need to remind them that there are the other side of the coin, and in order to have the coin, you need the both sides, right?
Are you suggesting a miniKanren?
Sorry?
That's a deep cut. I think that's the name of JetBrains' Gen AI tool.
Yeah. Actually, I met some people from JetBrains research here, and they shared their achievements in using modern AI for stuff. But yeah, I think that we can benefit from cooperation. So it should not be war, but friendship. So.
I might be misremembering, but I think Ed Kmet, his company is doing some mixing of AI with logic programming.
Oh yeah. Man, I wish I could give the spiel that Ed gives on that. I think he'd have a really nice answer on where he'd throw his money at, because he's maybe doing it.
I think there's definitely people looking into. Wow. There's definitely people looking into whether declarative programming generally is just easier for these LLM kind of things to deal with, just because there's half of the syntax and there's more of the actual meaning represented. So in a very vague, hand-wavy pitch, I could see that being explored more.
I like that, yeah. Nice, easy to do program synthesis, our style or some other way, if you just have nice declarative combinators. All right, the light's coming on, tells me the club's about to close for the night. I think can I thank our panelists for... And I think we should also thank Michael for all the work he's done in organizing this.
Well, we also want to thank Will Bird, who couldn't be here today. He did a lot of the organizing, and Jason Heeman for all the work he did on this as well. We're also organizing, if people want to go out to dinner tonight, we have a couple options for restaurants, people, if they're interested in going.
All right, see you guys 2026.